Welcome to the Late Lab. It's wonderful to have you here tonight. Before we wander into tonight's strange little corner of science, tell me, where are you watching from? Tucked under a blanket, half awake on the sofa, listening quietly while the room goes dark around you? Wherever this finds you, I hope you're settled, calm, and comfortably far away from anything that needs urgent attention. If you enjoy these slow, thoughtful journeys through science, a like and subscribe helps this small, sleepy channel keep drifting forward. And if you're already part of it, thank you, honestly. It means a great deal to have you here, night after night, thought after thought. Now I'll do my best not to make quantum entanglement sound too fascinating, which may be slightly difficult, because this is the bit of physics where two particles can behave as though they still belong to one shared reality, even when distance says they really ought to mind their own business. Very inconsiderate of them, scientifically speaking. So let's begin gently. What is quantum entanglement? And why does it seem like the universe is allowing a connection that should not exist? Most of the time, a connection is not mysterious. It is something that can be followed. A hand pushes a door, and the door opens. A bell is struck and sound moves through the air. A lamp is switched on, and light spreads across a room. A phone sends a signal through cables, towers, satellites, and invisible waves of electromagnetic energy, until a voice appears on the other side of the world. Even when the path is complicated, even when it is hidden behind walls or drifting through the sky, there is usually some route that can be traced. Something begins here, travels there, and produces an effect somewhere else. That is the familiar world. It is the world of contact, signals, pushes, pulls, forces, and shared histories. It is the world where things are connected because they touched, or because they exchanged energy, or because a message passed between them. It is also the world the human mind is extremely good at surviving in, which is useful, because nobody wants to calculate the deep structure of reality before catching a dropped mug. In this ordinary picture, distance matters. If two objects are far apart, then whatever connects them must cross the space between them. A shout takes time to travel through air. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes a little over 8 minutes. Even the fastest signal in the universe does not arrive everywhere instantly. The cosmos, as far as everyday experience suggests, does not allow influence to simply skip the journey. This is why quantum entanglement feels so strange from the moment it appears. It is not strange because two particles can be related. Related things are everywhere. Two fragments can come from the same explosion. Two clocks can be set together before being carried to opposite sides of a city. Two gloves can be packed into separate boxes, so that opening one box and finding a left glove immediately tells you the other box contains the right glove. Nothing supernatural is happening there. The answer was already settled. The information was hidden from you, not from reality. Entanglement is stranger than that. In quantum physics, two particles can be prepared in a shared state, then separated by a large distance. When one is measured, the result is correlated with the result found for the other. At first, that might sound like the glove example. Perhaps each particle simply carried a hidden instruction from the beginning, like a tiny sealed envelope saying what result it would give when tested. But the deeper experiments do not fit that simple picture. The correlations are stronger than ordinary hidden instructions should allow, and they depend on the kinds of measurements chosen. That is where the calm surface of common sense begins to ripple. Quantum entanglement is not a magic spell, not telepathy, and not a secret cosmic messaging service. It does not let one person send information faster than light. It does not mean that two particles are whispering across space like very tiny, very dramatic pen pals. The individual results of quantum measurements still contain randomness, and useful messages still require ordinary communication that obeys the speed limit set by light. And yet, something real remains. Entangled particles behave as though the best description belongs to the pair as a whole, not to each particle separately. The relationship is not merely a lack of human knowledge. It is built into the quantum state itself. That is the part that makes the title feel so uncomfortable. The connection should not exist if the universe is made only from independent objects carrying their own settled properties through space. But again and again, in carefully controlled experiments, nature behaves as though that old assumption is not quite right. For centuries, physics had moved in the opposite direction. It had made the universe seem more orderly, more mechanical, and more understandable. Isaac Newton's work in the 17th century gave physics one of its great classical visions. The same principles that described falling apples could describe the motion of the moon. The planets did not wander through the heavens by divine whim or celestial mood. They moved according to universal gravitation and laws of motion. The universe began to look like a vast machine, astonishingly elegant, but still a machine. Newton's physics did not answer every question, and it would later be reshaped by deeper theories, but its success was extraordinary. It taught generations of scientists to imagine nature as something predictable. If the positions and motions of objects were known well enough, then their future could, at least in principle, be calculated. Reality seemed to have a definite state at every moment, whether anyone looked at it or not. Then came James Clerk Maxwell in the 19th century, bringing electricity, magnetism and light into one grand description. Maxwell's electromagnetic theory showed that changing electric and magnetic fields could travel through space as waves. Light itself emerged as an electromagnetic wave, moving at a finite speed. This mattered enormously. Influence was no longer imagined as something that had to act instantly across empty space. Fields could carry energy and information from place to place, but they still had to travel. That classical picture was not crude. It was beautiful, powerful, and deeply successful. It gave the world engines, radio, electrical networks, optics, and a new understanding of the invisible architecture around every charged particle. It also strengthened the idea of locality. In physics, locality means that objects are affected by their immediate surroundings, or by influences that travel to them through space at limited speeds. Things do not simply affect distant things without some physical process connecting the two. Alongside locality sat realism. In this context, realism means the idea that physical properties exist with definite values before they are measured. A stone has a position. A planet has a speed. A compass needle points a certain way, whether or not anyone is admiring it. Measurement reveals what is already there. It may disturb things a little, especially if the instrument is clumsy, but it does not normally create reality from scratch. Locality, realism, and causality formed a comfortable triangle. Causes came before effects. Influences travelled through space. Objects possessed definite properties. This did not make the universe simple exactly, but it made it the right kind of difficult. Difficult like a clock with many gears, not difficult like a clock that waits until you look at it before deciding which gears it had all along. Quantum physics disturbed that confidence. Entanglement does not destroy physics. That is important. The world does not dissolve into nonsense. Experiments still give reliable results. Technologies still work. Predictions can be made with astonishing precision. Quantum theory is not a failure of order, but a deeper and less familiar kind of order. It keeps the discipline of science while quietly removing some of the assumptions that once made science feel intuitive. This is the central tension. Quantum entanglement preserves the reliability of physics, yet undermines the old idea that every object must always carry its own complete, independent set of definite properties before it is measured. The measurable world remains structured and lawful, but the foundation beneath it is not built in the plain mechanical way that classical intuition expected. The strangest connection in the universe did not appear as a lone curiosity. It grew from a wider crisis. At the beginning of the 20th century, light, heat, atoms, and measurement all began behaving in ways that classical physics could not fully explain. The old theories were not useless. They were still excellent within their proper domain. But at very small scales, nature was hinting that something quieter and stranger had been there all along. Entanglement is one of those hints. It is not a crack in reality. It is a crack in the older picture of reality. And through that crack, the universe begins to look much less like a machine made of separate pieces, and much more like a place where the deepest relationships cannot always be pulled apart. By the end of the 19th century, physics looked almost complete. Not finished in every small detail, of course. Science is rarely that tidy. But to many physicists, the broad shape of the universe seemed to be in place. The great pieces had settled together with an elegance that must have felt deeply reassuring. Isaac Newton's mechanics described motion, gravity, falling bodies, orbiting planets, and the steady sweep of celestial objects across the sky. James Clerk Maxwell's electromagnetic theory had united electricity, magnetism, and light into one magnificent structure. Thermodynamics explained heat, engines, pressure, temperature, and the strange but dependable rule that disorder tends to increase. It was a powerful vision. Matter moved according to laws. Forces acted in ways that could be calculated. Energy could change form, but it did not simply vanish. Light travelled as a wave through space. Heat behaved statistically, emerging from the restless motion of atoms and molecules. The universe was not simple, but it appeared understandable, difficult certainly. But difficult in the way a vast clockwork mechanism is difficult, not in the way a dream is difficult. There were still puzzles, but many of them seemed like loose threads rather than signs that the whole fabric might need to be rewoven. A more precise measurement here, a more careful theory there, and perhaps physics would become a polished cathedral of certainty. The physicist Lord Kelvin is often associated with this mood, though the famous idea that only small clouds remained over physics has become a little more complicated in retelling. Still, the feeling was real. Classical physics had been so successful that it was tempting to believe nature had almost run out of surprises. Nature very politely had not. One of the first cracks appeared in the study of blackbody radiation. A blackbody is an ideal object that absorbs and emits radiation perfectly. If heated, it glows, first dull red, then brighter, then toward white, and beyond. This was not an obscure curiosity. It was tied to heat, light, temperature, and the way matter exchanges energy with radiation. Classical physics should have been able to explain it smoothly. But when physicists tried to calculate the spectrum of radiation emitted by a blackbody, the old theory misbehaved. At shorter wavelengths, especially in the ultraviolet region, classical reasoning predicted that the emitted energy should rise without limit. In plain terms, the mathematics suggested an absurd flood of high-energy radiation that reality simply did not produce. This failure became known as the ultraviolet catastrophe, which sounds dramatic enough to be the name of a very anxious rock band, but it was genuinely serious. Max Planck found a way through it in 1900. He proposed that energy was not exchanged in any continuous amount but in tiny discrete packets. These packets came in sizes linked to the frequency of the radiation. Planck did not initially present this as a full revolution in the meaning of reality. It was, at first, a kind of desperate mathematical rescue, but hidden inside that rescue was the beginning of quantum theory. Energy, at the deepest level, seemed to come in steps. That was not how classical physics liked to imagine the world. A classical system could usually vary smoothly. A planet could have a little more speed or a little less. A wave could carry a little more energy or a little less. But Planck's idea suggested that nature did not always permit smooth changes. In certain situations, it allowed only particular amounts. The staircase had appeared beneath the carpet. Then Albert Einstein pushed the idea further in 1905. The puzzle was the photoelectric effect, where light shining on certain materials could knock electrons out of them. Classical wave theory expected that brighter light should eventually give electrons enough energy, whatever the colour of the light. But experiments showed something stranger. Below a certain frequency, light could be made brighter and brighter without freeing electrons. Above that frequency, electrons could be released even when the light was faint. Einstein explained this by treating light as if it arrived in packets of energy. These packets were later called photons. The energy of each photon depended on the light's frequency, not merely on its brightness. A low-frequency beam could deliver many photons, but if each photon lacked enough energy, no electron would be knocked free. A higher frequency photon could do the job. It was like trying to unlock a door with many soft feathers instead of one correctly shaped key. The feathers may arrive in impressive numbers, but the lock remains unimpressed. This was a profound step. Light had already been shown to behave like a wave, especially through interference and diffraction. Now it also seemed to behave like a stream of particles. The neat classical categories were beginning to bend. Light was not fitting comfortably into one box. Atoms soon made the problem deeper. Niels Bohr, in 1913, proposed a model of the atom in which electrons could occupy only certain allowed energy levels around the nucleus. They could jump between these levels by absorbing or emitting specific amounts of energy. This helped explain the sharp spectral lines seen when atoms emitted light. Instead of producing every possible colour in a smooth smear, atoms released light at particular frequencies, like musical notes from an instrument with very strict opinions. Bohr's model was not the final picture of the atom, but it revealed something essential. The microscopic world seemed governed by allowed states. Electrons were not tiny planets moving freely through every possible orbit in the classical way. Their behaviour came with restrictions, levels, and transitions. Quantum physics was not being invented because scientists fancied making the universe more peculiar. It was being forced into existence by experiments. Then the wave and particle confusion spread to matter itself. Louis de Broglie proposed that particles such as electrons could have wave-like properties. Erwin Schrödinger developed a wave equation that described how quantum states evolve. Werner Heisenberg created matrix mechanics, a different but equivalent formulation of quantum theory, built around observable quantities rather than visual pictures of tiny paths. Max Born then gave the wave function its probability interpretation, showing that it did not simply describe a material wave in ordinary space, but the probabilities of possible measurement outcomes. This was the deeper realization. Particles were not behaving like little billiard balls. Waves were not behaving like ordinary water ripples. Energy was not always smooth. Measurement was not always a passive act of revealing a pre-existing answer. The basic categories of classical physics were still useful in the everyday world, but they were no longer enough. Quantum mechanics did not begin with entanglement. It began with light refusing to be only a wave, electrons refusing to behave like tiny planets, atoms revealing discrete energy levels, and measurement becoming strangely central. Entanglement would later emerge from this new framework, not as a random oddity, but as one of its most unsettling consequences. Once particles were described by quantum states rather than fixed miniature objects with neatly settled properties, a new possibility opened. Two systems could share one mathematical description. Their properties could become linked in a way that could not be reduced to each system carrying its own private little instruction sheet. The old classical world had begun to crack, and through those cracks, physics was about to discover that the deepest connections in nature might not behave like connections at all. A particle in quantum physics is not described in quite the same way as a tiny bead moving through empty space. In ordinary life, it feels natural to imagine an object as having a clear position, a clear motion, and a clear set of properties even when nobody is watching it. A pebble on a path does not seem to need an audience before it decides where it is. A football flying through the air does not pause halfway across the pitch to consider whether it is behaving more like a wave today. It simply has a location, a speed, and a direction. This is the comfortable classical picture, and for everyday objects it works so well that questioning it can feel faintly rude. But in quantum mechanics, the most complete description of a system is called its quantum state. A quantum state is not a little glowing mist wrapped around the particle. It is not a visible cloud that could be photographed if the microscope were powerful enough and politely asked to try harder. It is a mathematical description of what can be known, predicted and measured about the system. It tells physicists the possible outcomes of measurements and the probabilities attached to those outcomes. That last word matters. Probabilities are not just a confession of ignorance in quantum theory. They are built into the way the theory works. In classical physics, a probability often means that some information is missing. A coin hidden under a cup is already heads or tails, even if nobody has looked. The uncertainty belongs to the person, not to the coin. Quantum uncertainty is different. Before measurement, certain properties are not always described as having one definite pre-existing value in the old classical sense. Instead, the quantum state contains a structured range of possible outcomes. This is where superposition enters the story. Superposition is often described as a particle being in two states at once, but that phrase can be misleading if it is taken too casually. A quantum system in superposition is not simply confused, indecisive, or wobbling between options like someone choosing biscuits in a supermarket aisle. Superposition is a real feature of the quantum state. It means that the system is described by a combination of possible measurement outcomes with specific probabilities attached to them. One example is energy. An atom can have particular allowed energy levels, and in some circumstances it can be placed into a superposition involving more than one energy state. Another example is polarization, a property of light that describes the orientation of its electromagnetic wave. A photon can be prepared so that a measurement of polarization has more than one possible result, with probabilities predicted by its quantum state. Then there is spin, one of the most important and easily misunderstood quantum properties. Particle spin sounds as though a tiny object is rotating, like a little planet turning on its axis. That image is tempting, but it is not correct. Spin is an intrinsic quantum property. It belongs to particles such as electrons in a way that has no exact everyday equivalent. It produces measurable effects, and it behaves mathematically like angular momentum, but an electron is not simply a tiny ball spinning through space. At the quantum scale, the universe has once again taken a familiar word and made it slightly less cooperative. Wolfgang Pauli played a crucial role in understanding spin and the structure of matter. His Pauli exclusion principle states that no two identical fermions, such as electrons, can occupy the same quantum state within a system. This principle helps explain the structure of atoms, the arrangement of electrons in shells, the chemistry of the periodic table, and even why ordinary matter does not simply collapse into itself. In a very real sense, the firmness of the chair, the shape of molecules, and the rich variety of chemistry owe something to this quiet quantum rule, not bad for something that cannot be pictured as a little spinning marble. One of the clearest demonstrations of quantum discreteness came from the Stern-Gerlach experiment, carried out by Otto Stern and Walter Gerlach in the early 1920s. In the experiment, a beam of silver atoms was sent through a non-uniform magnetic field. Classical expectations suggested that the atoms might be deflected in a smooth spread, because their magnetic orientations could point in any direction. But that is not what happened. The beam split into distinct parts. This mattered because it showed that measurement at the quantum level could produce discrete outcomes rather than a continuous range. The atoms did not land in every possible place, as a classical picture might have suggested. They behaved as though only certain measurement results were allowed. The Stern-Gerlach experiment became one of the great visual clues that quantum properties do not always slide smoothly from one value to another. Sometimes nature gives answers in steps. This is the setting in which entanglement begins to make sense, at least as much as it can be said to make sense without making the universe blush. If one quantum system can be described by a state, then two quantum systems can also be described by a state. Sometimes the state of the pair can be separated neatly into the state of one particle and the state of the other. In that case, each system can be treated, more or less, as having its own individual quantum description. But sometimes the combined state cannot be pulled apart that way. The best description belongs to the whole system. That is entanglement. Two or more quantum systems are entangled when their shared quantum state contains relationships that cannot be reduced to separate independent states for each part. The particles may be far apart, yet the combined description still matters. Measuring one system gives information about what can be expected when measuring the other, not because a message has necessarily flown between them at that instant, but because the pair was never fully described as two isolated things in the first place. This is already strange, but it becomes even stranger when compared with ordinary correlations. Imagine two sealed boxes, one containing a red card and one containing a blue card. If the boxes are mixed up and sent to different cities, opening one box and finding the red card instantly tells you the other contains the blue card. That looks like a distant connection, but really it is just hidden information being revealed. The cards had definite colours all along. Nothing mysterious has happened. The boxes have not communicated. The person opening the first box has simply learned something. Entangled particles can produce correlations that go beyond that kind of hidden card story. Their measurement results can be linked more strongly than classical hidden instructions allow. This does not mean they can send messages faster than light. It does not mean one particle is calling the other across space with urgent little quantum gossip. But it does mean that the old idea of each particle carrying a complete private instruction sheet becomes deeply difficult to maintain. That point will eventually become central to Bell test experiments, where physicists compare the predictions of quantum mechanics with the limits imposed by local hidden variable theories. But before experiments could settle anything, the conceptual problem had to become clear. Quantum mechanics was no longer merely saying that small objects were difficult to observe. It was suggesting that the properties of separated systems might not always belong to those systems independently. This raised a serious question. Was quantum mechanics a complete description of reality, however strange it appeared? Or was it only a temporary tool, useful for calculation, but hiding a deeper layer of ordinary classical facts underneath? That question would trouble some of the greatest physicists of the 20th century. It would lead directly into a debate about locality, reality, measurement, and whether the universe could truly allow two distant particles to share a state that refused to be divided. The older picture had imagined nature as a collection of separate things, each carrying its own settled properties through space. Quantum mechanics offered a quieter, stranger possibility. Sometimes the most important fact is not what each particle is by itself, but what the two are together. Albert Einstein helped create quantum physics, which makes his discomfort with it especially interesting. He was not standing outside the story, grumbling at a new idea because it was fashionable to grumble. Einstein had played a central role in revealing the quantum nature of light. His work on the photoelectric effect helped show that light could behave as if it arrived in packets of energy, later called photons. He understood better than almost anyone that the old classical picture could not survive unchanged. But as quantum theory developed, Einstein became increasingly uneasy about what the new theory seemed to be asking physicists to accept. His concern was not that quantum mechanics failed. That would have been easier. A theory that gives wrong answers can be repaired, replaced, or gently escorted from the building. Quantum mechanics gave astonishingly successful answers. It explained atomic spectra, chemical behavior, the behavior of electrons, and the strange patterns seen in experiments with light and matter. Its calculations worked. That was part of the problem. Einstein was troubled by the possibility that quantum mechanics worked while still being incomplete. It might be an excellent tool for predicting outcomes without being the final description of what reality was actually doing underneath. To Einstein, a physical theory should not merely tell scientists what they would observe. It should also describe a world that exists clearly and objectively, whether or not anyone is measuring it. Two ideas sat near the centre of his discomfort: locality and realism. Locality is the principle that objects are influenced directly by their immediate surroundings, or by signals and fields that travel through space at a limited speed. A cause here can produce an effect there, but something must cross the distance. A ripple travels across water, sound moves through air, light travels through space. Even gravity, in Einstein's general theory of relativity, does not update the whole universe instantly like an impatient announcement. Changes in the gravitational field propagate at the speed of light. Locality protects the order of cause and effect. It stops the universe from becoming a place where distant events can tug on each other without any clear physical route between them. It is one of the reasons physics feels like physics rather than a rumour mill with stars. Realism in this context is the idea that physical properties have definite values before they are observed. The moon is not waiting for someone to look up before having location. A stone has a mass whether or not it is being weighed. A planet has a path whether or not a telescope is pointed toward it. In the older classical view, measurement reveals properties that already exist. It may disturb a system slightly, especially at small scales, but it is not supposed to bring every property into being from nowhere. Einstein believed that a complete physical theory should preserve something like this. He did not demand that the microscopic world behave exactly like the everyday world. He was far too subtle for that. But he resisted the idea that reality itself might be fundamentally incomplete until measured, or that distant systems might be linked in a way that appeared to ignore ordinary separation. In 1935, Einstein sharpened this concern with Boris Podolsky and Nathan Rosen. Together they published a famous paper now known as the Einstein Podolsky Rosen paper. Its purpose was not to prove that quantum mechanics was useless. It was to argue that quantum mechanics, as it was then understood, could not be a complete description of physical reality. The argument considered two quantum systems that interact and then move apart. According to quantum mechanics, the systems may be described by one shared state. If a measurement is made on one system, the result can allow a prediction about the other distant system. The unsettling question is what this means. Did the distant particle already have the relevant property all along? If so, then perhaps quantum mechanics was missing hidden information. But if the property was not definite until measurement, then measuring one particle seemed to affect the description of the other immediately, even across a large distance. To Einstein, Podolsky and Rosen, this was unacceptable if quantum mechanics claimed to be complete. They argued that either the distant particle already possessed the property, or quantum mechanics implied a strange non-local effect. Since they wanted to preserve locality, they concluded that the quantum description must be incomplete. There had to be more to reality than the wave function was saying. This is where the phrase spooky action at a distance enters the story, though it is often handled a little carelessly. Einstein used the phrase to criticize what he saw as the troubling implications of quantum mechanics. He was not proposing a mystical force. He was not saying particles were communicating through ghostly channels. He was objecting to the idea that nature could contain this kind of apparent non-local connection at all. For Einstein, the problem was not spookiness as decoration. It was scientific seriousness. A theory that seemed to allow distant measurement choices to be linked without an ordinary causal bridge appeared, to him, to be missing something essential. Niels Bohr disagreed. Bohr responded to the Einstein-Podolsky Rosen argument from the viewpoint associated with the Copenhagen interpretation of quantum mechanics. The Copenhagen interpretation is not a single neat doctrine written on a stone tablet, which is probably for the best because physicists already have enough heavy things to carry, but broadly, it emphasizes the role of measurement, experimental arrangements, and the limits of applying classical language to quantum systems. Bohr argued that Einstein, Podolsky, and Rosen were asking for a kind of reality that quantum mechanics did not provide and perhaps did not need to provide. In Bohr's view, the meaning of a physical quantity could not be separated from the experimental context in which it was measured. The arrangement of the measuring device mattered, The question being asked of nature mattered. A quantum system did not always possess the kind of independent, definite properties that classical realism assumed. This was not a small disagreement. It was a clash over what physics was supposed to describe. Einstein wanted a theory that pictured an objective reality existing with definite features behind a measurement. Bohr was more willing to accept that quantum theory set limits on what could meaningfully be said about microscopic systems before measurement. Einstein worried that this gave up too much. Bohr believed Einstein was demanding classical clarity from a world that had already shown it did not operate by classical rules. Entanglement sat at the heart of the argument because it exposed the tension so clearly. If two particles share one quantum state, and if measuring one allows strong predictions about the other, then the old picture of separate objects with independent properties begins to strain. The particles may be far apart, yet quantum mechanics treats the relationship between them as part of the most complete description. That is why entanglement looked like a connection that should not exist. It challenged locality by making distant systems seem linked in a way no ordinary signal could explain. It challenged realism by suggesting that properties might not be fully definite before measurement. And it challenged the comforting belief that the universe could always be understood as separate pieces carrying private facts through space. Einstein's unease was not a failure of imagination. It was a sign that he understood the stakes very clearly. If quantum mechanics was complete, then reality was not merely smaller, faster, or harder to observe than classical physics had imagined. It was built on principles that disturbed the very meaning of separation. The debate did not end with Einstein and Bohr. For a long time it remained suspended between philosophy and physics, like a question too sharp to sleep peacefully. Quantum mechanics kept working. Einstein kept doubting. Bohr kept defending the strange new framework. And quietly, beneath the argument, entanglement waited for the moment when someone would find a way to test whether the impossible connection was only a misunderstanding, or whether the universe really was stranger than even Einstein wanted it to be. The argument over quantum mechanics did not stay neatly between Einstein and Bohr. It spread into the thoughts of other physicists who understood that something unusually deep was being exposed. One of them was Erwin Schrödinger, the Austrian physicist whose wave equation had become one of the foundations of quantum theory itself. Schrödinger was not an outsider looking in. He had helped build the new physics. His wave equation gave scientists a powerful way to describe how quantum states change over time, and it became central to the understanding of atoms, particles, and the strange wave-like behavior of matter. Yet Schrödinger, like Einstein, was not entirely comfortable with what quantum theory seemed to imply. He saw that the mathematics worked, but he also saw that the meaning of the mathematics was far from simple. After the Einstein Podolsky Rosen paper appeared in 1935, Schrödinger responded with a series of writings that explored the strange consequences of shared quantum states. It was in this context that he introduced the word entanglement. The term was not chosen for decoration. It captured something essential. Two quantum systems could become described in such a way that their properties were no longer fully separable. The parts could not always be treated as independent objects, each carrying its own complete private description. Schrödinger saw this as one of the defining features of quantum mechanics, not a minor side effect, not a small technical curiosity tucked away in the mathematics. Entanglement to him revealed the heart of what made quantum theory different from classical physics. When two systems interact, their quantum descriptions can become bound together. After that, even if the systems move far apart, the most complete description may still belong to the combined whole rather than to each piece separately. This was a quiet but enormous shift. Classical physics had usually encouraged a simple way of thinking: understand the parts, and then build up the whole. Study the motion of each planet, each billiard ball, each molecule, and then combine the information. Of course, large systems could be complicated. A storm, a living body, or a galaxy could involve far too many moving pieces for easy calculation, but in principle, the whole was built from the individual facts of the parts. Entanglement disturbed that principle. It suggested that, at the quantum level, the whole could possess a description that could not be reduced to separate descriptions of the parts. The relationship itself was not merely an extra detail, it was part of the physical description. At first, this can sound similar to ordinary correlation. Everyday life is full of correlations, and they are not mysterious. If a pair of gloves is separated into two boxes, and one box is sent to London while the other is sent to Tokyo, opening the first box and finding the left glove immediately tells you that the other box contains the right glove. No signal has crossed the world. No invisible influence has travelled between the gloves. The gloves had their handedness all along. Someone simply learned which one was where. A pair of matching cards works the same way. If one person receives the red card and another receives the black card, checking one card reveals information about the other. Again, nothing strange has happened. The result was fixed before anyone looked. The uncertainty belonged to the people who had not yet opened the envelopes, not to the cards themselves. These comparisons are useful because they show what entanglement is not. Entanglement is not simply the discovery that two things can share a past. It is not just the surprise of opening one box and learning what must be in another. In the quantum case, the correlations can be stronger and more subtle than any story based only on pre-written hidden instructions. The choice of what is measured matters, and the patterns of results cannot be explained by the simplest classical idea that each particle merely carried a definite answer from the beginning. This is why entanglement feels so unsettling. It does not behave like a normal secret waiting to be uncovered. It behaves as if the two systems share a deeper state, one that only gives definite answers when specific measurements are made. The particles are not necessarily sending messages to each other. They are not chatting across space like tiny experimental troublemakers. But they also do not fit comfortably into the idea of two separate objects with all their properties settled in advance. Schrödinger made this difficulty even more famous with another thought experiment in 1935, Schrödinger's cat. The cat was imagined inside a sealed box with a quantum event that could trigger a chain of events leading to the cat being alive or dead. The purpose was not to suggest that physicists should start placing cats into boxes, which would be an unpopular research program for many good reasons. It was designed to show how strange quantum superposition becomes when its logic is extended toward ordinary large objects. In quantum theory, a microscopic system can be placed into a superposition of possible states. But if that microscopic system becomes connected to a larger system, such as a measuring device, then the mathematics seems to spread the superposition outward. Schrödinger used the cat to ask a sharp question. If the quantum event is in a superposition, and the cat's fate depends on it, should the cat also be described as somehow both alive and dead until the box is opened? The point was not that real cats drift about in useful laboratory superpositions. Large, warm objects interact constantly with their surroundings. Air molecules, thermal radiation, vibrations, and countless microscopic contacts rapidly entangle them with the environment. This process is now called decoherence. Decoherence destroys the visible quantum interference that would be needed for a large object to behave like a clean quantum superposition in practice. A cat is much too large, warm, and environmentally entangled to function like an isolated electron or photon. It is also, one hopes, too dignified. But Schrödinger's cat still served its purpose. It exposed the measurement problem. It showed that quantum theory was not just a strange method for calculating small experimental results. It raised a deeper question about what physical reality is like before measurement, and how the definite world of experience emerges from a theory built on probabilities and superpositions. This was the same deeper issue revealed by entanglement. Quantum mechanics could predict results with extraordinary accuracy, but what was it describing? Was the wave function a complete physical description? Was it a tool for prediction? Did particles possess definite properties before measurement? Or did measurement play a more fundamental role than classical physics had allowed? Schrödinger's thinking shifted the mystery from one particle to whole systems. Entanglement showed that the universe could not always be understood by neatly separating one object from another. The cat thought experiment showed that measurement could not be brushed aside as a minor detail. Together they made the foundations of quantum theory feel less like a technical problem and more like a quiet challenge to the old meaning of reality. For decades, these questions remained partly philosophical. Quantum mechanics kept working. Laboratories kept confirming its predictions. Engineers and physicists used it to understand atoms, materials, light, and chemistry. Yet the question of entanglement remained strangely suspended. Was it proof that nature really abandoned classical separability, or was it only a sign that quantum mechanics was missing hidden details? The mystery had a name now. It had shape. It had arguments wrapped around it. But it still needed something more decisive. It needed a way to be tested. For a long time, entanglement sat in an awkward place. It was not ignored. It was too important for that. Einstein, Podolsky, Rosen, Bohr, and Schrödinger had all seen that something unusually deep was hidden inside the quantum description of separated systems. But the debate had a peculiar quality. It seemed to hover between physics and philosophy. Quantum mechanics predicted the results of experiments beautifully, yet the meaning of those predictions remained unsettled. Was the theory revealing a strange feature of reality itself, or was it merely hiding a deeper, more ordinary mechanism beneath its probabilities? Then John Stuart Bell changed the shape of the question. Bell was a Northern Irish physicist who worked at the European Organisation for Nuclear Research, commonly known as CERN. In 1964, he published a result that became one of the most important discoveries in the foundations of quantum mechanics. It is now called Bell's theorem. Its power was not that it made quantum mechanics stranger. Quantum mechanics was already doing a splendid job of being strange without assistance. Bell's achievement was that he found a way to make the argument testable. Before Bell, it was possible to imagine that Einstein had been right in an important way. Perhaps quantum mechanics was incomplete. Perhaps particles really did carry hidden information that determined what would happen when they were measured. The randomness of quantum theory might then be a sign of missing knowledge, not a fundamental feature of nature. The particles would know their answers in advance, while physicists, poor things, would only discover them later. This idea belongs to a family of explanations called local hidden variable theories. The word local matters. A local theory preserves the idea that distant events cannot directly influence each other faster than light. If one particle is measured on Earth and another is measured far away, the result here should not instantly reach across space and alter the result there. Any influence must travel through the space between them, obeying the speed limit built into relativity. The hidden variable part means that the particles may carry extra information not included in the ordinary quantum state. These hidden details would determine the outcomes of measurements. From the outside, the results might look random, but underneath, they would be fixed by properties the theory had not yet revealed. It is a comforting idea in a way. It allows the universe to keep its old classical dignity. No instant influence. No unsettling dependence on measurement, no particles behaving like they have mislaid their own identities. Bell asked what such a world would actually allow. He showed that if local hidden variable theories were correct, then there would be limits on how strongly the results of distant measurements could be correlated. These limits are known as Bell inequalities. The precise mathematics can become technical, but the main idea can be spoken gently enough. If two separated particles simply carry pre-written instructions, and if no faster-than-light influence passes between them, then their measurement results can match or differ only within certain boundaries. There is only so much coordination that hidden instruction sheets can produce. Imagine two performers sent to opposite sides of the world with sealed scripts. They are not allowed to communicate once separated. If later they answer questions in remarkably matching ways that might be explained by the scripts they carried. But there are limits. If the questions can be varied in different ways, and the answers keep showing patterns too strong and too flexible for any prearranged script, then the script explanation begins to fail. Bell's theorem gives physics a version of that limit. Quantum mechanics predicts that for certain entangled states, the correlations between separated measurements can violate Bell inequalities. In other words, the results can be too strongly linked to fit any ordinary local hidden instruction model. The particles do not behave as though each one simply carried a complete private list of answers from the beginning. This is a very careful kind of impossibility. Bell's theorem does not simply say that one particle sends an instant message to the other. That would be a tempting shortcut, but it would be too crude. Quantum entanglement does not allow useful faster-than-light communication. A measurement on one particle cannot be controlled to send a chosen message to the other side of space. The individual outcomes still appear random. What Bell's theorem shows is subtler and deeper. If the predictions of quantum mechanics are correct, then at least one comfortable classical assumption cannot remain unchanged. Locality, realism, or a related assumption about the independence of measurement choices must give way in some form. The old picture cannot have everything it wants. It cannot keep particles with fully pre-existing answers, preserve strictly local influences, and still match the quantum predictions for entangled systems. That was the brilliance of Bell's work. He did not merely take sides in the Einstein and Bohr debate. He sharpened the debate until it became experimentally vulnerable. Philosophy, which had been floating rather elegantly in the upper atmosphere, was brought down into the laboratory, handed measuring devices, and asked to behave itself. This changed the status of entanglement. It was no longer only a troubling feature in the mathematics of quantum theory. It became something that could be investigated through real measurements. If experiments found that Bell inequalities were obeyed, Einstein's hope for local hidden variables would gain strength. If experiments found that Bell inequalities were violated, then the quantum view would become much harder to dismiss as merely incomplete bookkeeping. Bell himself was careful about what his theorem meant. He knew the issue was not solved by slogans. The theorem did not explain exactly what reality was doing behind the scenes. It did not choose one interpretation of quantum mechanics and crown it forever, but it showed that nature could not be comfortably squeezed back into the old classical frame without paying a serious price. That is why Bell's theorem became one of the great bridges in modern physics. On one side stood the foundational arguments of Einstein, Bohr, and Schrödinger, full of questions about reality, measurement, and separability. On the other side stood experiments with photons, atoms, detectors, and carefully chosen measurement settings. Between them was Bell's insight. The impossible connection could leave a measurable trace. The connection that should not exist was no longer just an unsettling thought. It had become a question the universe could answer. Bell's theorem gave physicists a way to ask nature a sharper question. But a theorem, by itself, is not the same as an experiment. It can show what should be true if certain assumptions hold, and it can show what quantum mechanics predicts instead. But sooner or later, the universe has to be invited into the conversation, preferably with lasers, detectors, and a room full of people trying not to trip over cables. In the 1970s, John Clauser and Stuart Friedman performed one of the first important experimental tests of Bell's ideas. They used pairs of entangled photons produced from calcium atoms, then measured the photons in ways that could test whether their correlations obeyed or violated a Bell inequality. The results supported the predictions of quantum mechanics. The photons behaved more like entangled quantum systems than like tiny objects carrying ordinary hidden instruction sheets. This was a major step. It did not end every possible objection, because early experiments are rarely perfect. But it showed that Bell's theorem was not just an elegant argument written in the quiet corners of theoretical physics. It could be brought into the laboratory. The strange question that had once seemed almost philosophical could be tested with real light, real instruments, and real statistics. Then, in the early 1980s, Alain Aspect and his collaborators in France performed a series of increasingly refined Bell test experiments using entangled photons. These experiments became landmarks in the history of quantum physics. Aspect's team improved the control of the measurement process and tested the correlations predicted by quantum theory with greater sophistication. Again, the results favoured quantum mechanics over local hidden variable explanations. The importance of these experiments is easy to miss if the story is told too quickly. They were not simply proving that quantum physics was weird, which by that point was less a discovery and more a recurring personality trait. They were testing whether the strange correlations of entangled particles could be explained by a more familiar kind of hidden reality underneath. If the particles had carried prearranged answers, and if no influence could travel faster than light, then the results should have stayed within Bell's limits. Instead, the experimental results matched the quantum prediction. The correlations were too strong for the simplest local hidden variable picture. Still, careful physicists do not usually accept a deep conclusion after one clean-looking result and then immediately put the kettle on. They look for loopholes. An experimental loophole is a possible weakness in a test that might allow a non-quantum explanation to survive. One of these is the detection loophole. If not every particle is detected, then perhaps the measured particles are not a perfectly fair sample of all the particles produced. Another is the locality loophole. If the measurement choices and outcomes are not separated carefully enough in space and time, then some ordinary signal might in principle influence the result. There is also the freedom of choice loophole, which concerns whether the measurement settings are genuinely independent of the hidden variables being tested. These loopholes do not mean the experiments were useless. They mean that physics is a discipline that gets nervous in a productive way. It asks whether nature has been cornered fairly, or whether some small escape route has been left open behind the equipment cabinet. Over the following decades, experiments became more precise. Researchers developed better photon sources, faster switching methods, improved detectors, and more careful designs. Later loophole-reduced Bell tests were performed by groups at Delft University of Technology, the National Institute of Standards and Technology, and the University of Vienna. These experiments used different physical systems and carefully arranged conditions to close major loopholes at the same time. The Delft experiment, for example, used entangled electron spins associated with defects in diamond, separated far enough that the relevant measurement events could not easily influence each other by ordinary signals. Other groups used highly efficient detectors and entangled photons to strengthen the case further. The details vary, but the broad purpose was the same: remove as many reasonable classical escape routes as possible, then see whether nature still violates Bell inequalities. It did. Modern Bell tests have not made entanglement feel ordinary. That is perhaps the most quietly amusing part of the story. Usually repeated experiments make a phenomenon seem less strange. Lightning becomes electricity. Disease becomes microbes, cells, and immune response. The rainbow becomes optics. But entanglement is different. The more carefully it is tested, the harder it becomes to dismiss, yet the less comfortably it fits the old picture of separable reality. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, the violation of Bell inequalities, and pioneering work in quantum information science. The award recognized not only a set of brilliant experiments, but also a transformation in how physicists understood entanglement. What had once been treated by some as a philosophical irritation had become a measurable resource, a laboratory reality, and one of the foundations of modern quantum technology. The conclusion is not that Einstein was foolish to worry. Quite the opposite. His discomfort pointed directly at one of the deepest problems in physics. The experiments show that the worry was not based on confusion, but on a real fracture between classical intuition and quantum behavior. Entanglement does not look like ordinary connection because it is not ordinary connection. The world revealed by Bell tests is not lawless. It is not mystical. It does not allow anyone to send a message instantly across the galaxy, which is disappointing for science fiction and probably useful for causality. But it does show that distant quantum systems can display correlations that cannot be explained by simple, local hidden instructions. Reality has been cornered, at least on this point. Entanglement is not merely a misunderstanding. It is not a measurement artifact. It is not a philosophical shadow cast by bad language. It is a real feature of the physical world. And that leaves a new question glowing quietly in the dark. If entanglement is real, and if distance does not erase the correlation, why does it not break the speed limit of the universe? At first glance, entanglement seems to threaten one of the most important rules in modern physics. If two particles can be separated by a vast distance, and a measurement of one is linked with a measurement of the other, it is natural to wonder whether something has travelled between them instantly. Perhaps one particle sends a message. Perhaps the other receives it. Perhaps somewhere beneath the equations, the universe has found a sneaky little shortcut around the speed of light, like a cosmic pedestrian ignoring a very serious road sign. But this is not what entanglement allows. The speed of light limit comes from Albert Einstein's special theory of relativity, published in 1905. Special relativity showed that space and time are not separate fixed backgrounds, but are woven together in a way that depends on motion. It also revealed a deep speed limit built into the structure of nature. Light in a vacuum travels at about 300,000 kilometers per second, and no usable information or causal influence can travel faster than that. This does not only apply to light itself, it applies to any signal that carries meaning from one place to another. A radio wave, a laser pulse, a gravitational disturbance, a command sent across a spacecraft network, or a simple flash used as a signal, all obey the same limit. If something can be used to send a controllable message, then relativity says it cannot outrun light. That is why entanglement seems alarming. Bell test experiments show that entangled particles can have correlations too strong for ordinary local hidden instruction models. Distance does not erase those correlations. The particles may be separated across a laboratory, across kilometers of fiber optic cable, or in principle across far greater distances, and the quantum relationship still matters. It sounds at first as if one particle must somehow be telling the other what happened. But quantum mechanics blocks that tempting interpretation in a very important way. A measurement result on an entangled particle cannot be controlled to send a chosen message. This is the heart of the no communication theorem. In plain language, the theorem says that entanglement by itself cannot be used to transmit information faster than light. When someone measures one particle from an entangled pair, the result they get is not something they can choose. It appears random. They cannot decide, this result will mean yes, and force the particle to produce it. They cannot tap out a message across the universe by choosing a pattern of quantum outcomes. The particle is not a telegraph key. It is not a phone. It is not even a very unreliable text message service. The strange part is that when the two observers later compare their results, they discover a pattern. The results are correlated in exactly the way quantum mechanics predicts. But that comparison requires ordinary classical communication. One observer must send their measurement record to the other, or both records must be brought together. That message travels by light, radio, cable, or some other normal method, and it cannot move faster than the speed of light. So the correlation is real, but it is not a usable signal. A careful example can help. Imagine two people in distant cities opening envelopes. If each envelope contains a card and one person finds red while the other finds blue, the first person instantly knows what the other card must be. But this is ordinary correlation. The cards had their colours before the envelopes were opened. No communication is needed and nothing quantum has happened. Entanglement is stranger than this because the particles are not simply behaving like cards with pre-written answers. Bell's theorem and Bell test experiments show that the correlations cannot be explained by the simplest local hidden instruction story. But entanglement still does not become communication. It gives a relationship between results, not control over results. This distinction is subtle, but it is essential. Correlation means that two sets of outcomes are linked in a pattern. Communication means that one side can choose something and make the other side receive that chosen information. Entanglement gives the first, not the second. The universe permits the strange pattern, but refuses to let anyone turn it into a faster-than-light message. Very impressive. Also slightly annoying if anyone was hoping to cancel their broadband provider. This is how quantum mechanics and special relativity coexist. Not comfortably perhaps, but successfully. Entanglement challenges classical separability, the old idea that distant objects must always have fully independent descriptions. It suggests that the combined quantum state of two systems can matter even when the systems are far apart. But because the individual results remain uncontrollable, entanglement does not create causal signals that violate special relativity. In other words, quantum theory bends the old intuition about what it means for two things to be separate, while relativity protects the order of cause and effect. There is no usable faster-than-light influence. There is no cosmic telephone. There is no way to send a warning instantly to a distant star system that someone has, regrettably, left the oven on. And yet the mystery does not disappear. If entanglement is not a signal, then what is it? If one particle is not sending a message to the other, why do the results line up so strongly when measured and compared? If the outcomes are random individually, why does the pair reveal such a precise pattern together? These questions show that the deepest issue is not only distance, it is measurement. Quantum mechanics does not merely ask where particles are or how fast they move. It asks what can be meaningfully said about a system before measurement, what happens when a measurement is made, and why a world described by probabilities gives rise to definite outcomes when observed. Entanglement makes those questions sharper because it spreads the puzzle across separated systems. The speed of light remains safe. Causality remains intact. Signals still take time to travel. The universe does not allow information to leap instantly from one side of space to the other. But beneath that reassuring surface, entanglement leaves something unresolved. It shows that the old picture of independent objects carrying complete private properties through space is not enough. The connection cannot be used like a message, yet it cannot be dismissed as ordinary ignorance either. The real puzzle is not that quantum entanglement breaks the rules of relativity. It is that it obeys those rules while still refusing to behave like anything classical physics expected. Measurement is where quantum physics becomes most difficult to ignore. Before measurement, a quantum system is described by a quantum state. That state gives the possible outcomes that may be found, along with the probabilities for those outcomes. But when a measurement is actually made, the result is not a soft blur of possibilities. A detector clicks. A spot appears on a screen. A photon is found with one polarization rather than another. An electron's spin is recorded as one definite result. Reality, at least as it appears in the laboratory, gives an answer. This is quantum measurement, the process by which a quantum system produces a definite observed result. It sounds simple when said quickly, but it is one of the deepest problems in the foundations of quantum mechanics. The theory is extremely good at predicting the probabilities of what will be observed. It is much less obvious what exactly counts as a measurement, why one particular result appears, and how the rich spread of possible outcomes becomes the single result experienced in the world. Max Born gave one of the essential rules for understanding this. The Born rule says that the wave function does not usually give simple certainties. It gives probabilities for different measurement outcomes. If a quantum system is prepared in a particular state, the Born rule tells physicists how likely each possible result is when a chosen measurement is performed. This was a major shift from the older classical view. In classical physics, probability often reflects missing information. If a coin is hidden under a hand, it is already heads or tails. The uncertainty belongs to the observer. In quantum mechanics, the probabilities described by the wave function appear to be more deeply woven into the physical description itself. The theory does not simply say, the answer is there, but unknown. It says more carefully, These are the possible answers, and these are the probabilities with which they may appear. That is unsettling, because experiments do not show probabilities directly. They show outcomes. The detector does not politely say, "There was a strong chance of this." It clicks in one place. The atom emits one photon. The spin measurement gives one result. The world, in the moment of observation, seems to settle. One way of describing this transition is called wave function collapse. In this picture, the quantum state appears to shift from a spread of possible outcomes into the one result actually observed. Before measurement, the system may be described by a superposition. After measurement, one outcome is recorded. Collapse is the name often given to that apparent change. But wave function collapse is not understood in the same way by every interpretation of quantum mechanics. In some views, collapse is treated as a real physical process. In others, it is a useful update in knowledge after a measurement result is known. In the many worlds interpretation associated with Hugh Everett, the universal wave function does not collapse at all. Instead, different outcomes are treated as parts of a larger branching description. In de Broglie-Bohm theory, associated with Louis de Broglie and David Bohm, particles have definite positions guided by a quantum wave. The experimental predictions may match, but the story behind measurement changes depending on the interpretation. Entanglement makes measurement even stranger. When two particles are entangled, the best quantum description belongs to the pair as a whole. If one particle is measured, the result helps determine what should be expected when the other particle is measured. This remains true even if the two are far apart. Yet the first measurement cannot be controlled to send a chosen message to the second. The result is individually random. Only later, when both observers compare their records through ordinary communication, do the correlations become visible. So entangled measurement creates a peculiar balance. It does not break the speed of light. It does not allow a usable signal to leap across space. But it does show that the outcomes of separated measurements are not behaving like ordinary independent events. The two particles reveal a shared pattern that cannot be explained by simple, local, hidden instructions. This is where the measurement problem becomes more than a technical puzzle. It asks what kind of reality quantum physics is describing. Are measurement outcomes created in the act of measurement? Are they selected from a deeper hidden structure? Are all possibilities somehow retained in a wider universal wave function? Or is the question itself partly shaped by trying to force quantum nature into classical language? There is also another key idea: decoherence. Decoherence is the process by which a quantum system loses visible interference effects through interaction with its environment. Dieter Zär was one of the early physicists to emphasize this idea, and Wojciech Zurek developed it further in influential work on the quantum to classical transition. The basic point is that quantum systems do not remain perfectly isolated in everyday life. They interact with air molecules, light, heat, vibrations, surrounding matter, and countless other tiny influences. These interactions spread quantum information into the environment. The delicate phase relationships that allow superposition and interference become practically impossible to observe. The system starts to behave, for all ordinary purposes, like a classical object with definite features. This helps explain why tables, cats, teacups, and tired humans do not visibly exist in delicate laboratory-style superpositions. They are warm, large, and constantly entangled with their surroundings. The environment is always watching, in a physical sense, even if it is not taking notes in a tiny lab coat. Decoherence is powerful because it explains why quantum weirdness becomes hidden in the everyday world. It shows how classical-looking behavior can emerge from quantum rules without requiring those rules to stop working. But decoherence does not solve every philosophical question. It explains why different possible outcomes stop interfering with each other. It does not, by itself, fully explain why one particular outcome is experienced rather than another. This is why laboratories that study entanglement must be so careful. Fragile quantum systems have to be protected from noise, heat, vibration, stray electromagnetic fields, and unwanted contact with the environment. Photons may be guided through carefully aligned optical systems. Ions may be trapped in electromagnetic fields. Superconducting qubits may be cooled close to absolute zero. The aim is not to make nature mysterious, but to stop ordinary surroundings from washing the mystery away too quickly. Measurement, randomness, and decoherence reveal why entanglement is both real and delicate. The connection survives only when quantum systems remain isolated enough to preserve their shared state. The moment the environment becomes too involved, the fragile pattern spreads outward and becomes almost impossible to recover. Entanglement is not only about distance, it is about what happens when reality is asked a question, and why the answer arrives as one definite fact from a theory built out of possibilities. Entanglement may sound like something nature reveals only by accident, as if physicists have to wait patiently for two particles to become mysteriously linked, while the laboratory lights flicker in a suspiciously cinematic way. But in real science, entanglement is not only discovered, it is made. Modern laboratories can deliberately create entangled systems, guide them, measure them, and sometimes preserve them long enough to use them. This is one of the reasons entanglement moved from the edges of philosophical debate into the center of experimental physics. It is not merely a strange prediction written into equations. It can be produced on an optical table, inside a vacuum chamber, in a chip cooled to extreme temperatures, or in carefully controlled atoms held almost motionless by fields and lasers. One of the most important routes into laboratory entanglement uses photons, the quantum particles of light. Photons are useful because they can travel long distances, move through optical fibers, pass through lenses and crystals, and be detected with highly sensitive equipment. They are also naturally suited to experiments involving polarization. Polarization describes the orientation of a light wave's electric field, and for a single photon, it becomes a quantum property that can be measured in different ways. In a classical picture, two separated light particles might be expected to carry their own fixed properties, like tiny travelers with sealed passports. But entangled photons can be prepared so that their polarization measurements show correlations stronger than classical physics allows. If one photon is measured with a certain polarization result, the other photon's result will be linked in a way that fits the shared quantum state. The strange part is that this link cannot be explained by simply saying each photon carried a neat list of pre-written answers from the beginning. A common method for producing entangled photon pairs is called spontaneous parametric down conversion. The name sounds like something that belongs on a very serious machine with too many warning stickers, but the basic idea can be made gentle. A higher energy photon, often from a laser, enters a special nonlinear crystal. Inside that crystal, there is a small chance that the incoming photon will be converted into two lower energy photons. These two outgoing photons can be born with linked properties, such as polarization, momentum, or energy. The crystal does not produce a pair every time. Much of the incoming light passes through without doing the useful quantum trick, but with the right setup, enough entangled photon pairs are produced for experiments. Scientists then use mirrors, beam splitters, polarizers, detectors, and careful timing electronics to measure the photons and compare their results. The laboratory may look like a maze of optical components, but every piece is there to ask the particles a carefully controlled question. Anton Zeelinger's experimental work with entangled photons helped make this field famous. At the University of Vienna and through collaborations with other researchers, Zeilinger and his teams explored some of the most important consequences of entanglement, including quantum teleportation and long-distance tests of quantum correlations. Their experiments did not teleport objects in the science fiction sense, and nobody emerged from a glowing booth looking startled. Instead, they demonstrated that quantum information could be transferred from one system to another using entanglement together with ordinary classical communication. These photon experiments showed that entanglement could be controlled across increasing distances. Photons have been sent through optical fibers across free space and even used in satellite-based quantum experiments by other research groups. The wider lesson is that entanglement is not confined to a single tabletop experiment. It can be distributed, tested, and used as a resource, although always with great care, because quantum states are fragile and easily disturbed. Photons are not the only systems scientists can entangle. Atoms and ions can also be placed into shared quantum states. An ion is an atom or molecule with an electric charge, and because it is charged, it can be held in place by electromagnetic fields. In trapped ion experiments, researchers use carefully tuned lasers to cool ions, control their internal states, and entangle them with one another. The result is a kind of quantum choreography, though the dancers are extremely small and require a lot of equipment to stay in step. David Wineland, whose work at the National Institute of Standards and Technology helped pioneer precision control of trapped ions, showed how individual quantum systems could be manipulated with extraordinary accuracy. Rainer Blatt and his collaborators also made major contributions to trapped ion quantum control and entanglement, especially in Europe. These experiments helped demonstrate that entanglement could be engineered not just between flying photons, but between particles held in place and manipulated almost one by one. Trapped ions are valuable because they can be extremely well isolated from the environment. Their quantum states can remain coherent long enough for precise measurements and operations. But they are demanding systems. They often require ultra-high vacuum, laser cooling, carefully shielded conditions, and exquisite control. In other words, entanglement is possible, but it prefers a very calm workplace. Unfortunately for it, laboratories are run by humans, cables, power supplies, and the occasional mysterious vibration nobody wants to admit came from a nearby door. Another major platform uses superconducting qubits. These are not natural particles in the same way as photons or electrons. They are artificial quantum systems built from circuits that behave quantum mechanically when cooled to extremely low temperatures, often close to absolute zero. Research groups and companies such as IBM, Google Quantum Artificial Intelligence, and many academic laboratories use superconducting qubits to study quantum computing and controlled entanglement. In these devices, electrical currents and microwave signals are used to prepare, manipulate, and measure quantum states. Qubits can be entangled with neighboring qubits on a chip, allowing researchers to create increasingly complex quantum states. The engineering challenge is enormous. Superconducting qubits are sensitive to noise, heat, stray fields, imperfections in materials, and unwanted interactions with their surroundings. A quantum computer is not powerful because its qubits are dramatic. It is powerful when it works, because their delicate relationships are carefully protected and controlled. Across all these systems, the same theme returns. Entanglement is real, but it is not rugged. It does not behave like a steel cable connecting two objects across space. It is more like an exquisitely balanced pattern in the quantum state, easily blurred by environmental contact. Heat, vibration, random electromagnetic noise, imperfect detectors, and stray interactions can destroy the visible quantum behavior through decoherence. This fragility explains why building technologies based on entanglement is so difficult. Creating an entangled pair is already a careful task. Preserving that entanglement, measuring it accurately, using it for communication or computation, and scaling it up to many particles or qubits is much harder. Every extra component is another chance for the environment to interfere. Every longer distance is another opportunity for loss. Every larger system becomes more vulnerable to errors, and yet the progress is extraordinary. What once seemed like a philosophical puzzle about distant particles has become a practical laboratory skill. Scientists can create entangled photons in crystals, entangle trapped ions in vacuum chambers, link superconducting qubits on chips, and test the limits of quantum theory with astonishing precision. The connection that should not exist has become something that can be made on purpose. But that does not make it ordinary. It makes it even more remarkable. Entanglement is not a vague mystery hiding beyond experiment. It is a measurable, controllable, intensely delicate feature of nature. The universe allows this strange connection, but only under conditions that must be prepared with care. It is one of the deepest relationships in physics, and also one of the easiest to ruin by letting the ordinary world get too close. A particle can be imagined as a tiny thing, and for a long time, that was the natural way to think about it. An electron was a small charged object. A photon was a particle of light. An atom was a little structure made from smaller parts. Even when quantum physics made these objects strange, it was still tempting to picture them as things first, and only then ask what those things were doing. Where is the particle? How fast is it moving? What energy does it have? What path did it take? These were familiar questions, even when quantum theory answered them in unfamiliar ways. But as quantum mechanics developed, another way of thinking became impossible to ignore. A quantum system is not only a physical object, it is also a carrier of quantum information. That phrase needs to be handled carefully, because information can sound vague, almost ghostly, as if particles are carrying thoughts, meanings, memories, or tiny philosophical opinions about the universe. Quantum information is not that. It is not consciousness stored in matter. It is not hidden intention. It is not a particle quietly knowing the secrets of reality, while refusing to share them unless someone builds an expensive detector. Quantum information means precise physical information, described by quantum theory. It concerns the state of a system, the possible measurement outcomes, the probabilities of those outcomes, and the relationships that can exist between systems. It is information in the disciplined scientific sense, something that can be prepared, transformed, measured, compared, protected, lost, or transmitted according to physical rules. The basic unit of quantum information is called a qubit. A classical bit used in ordinary computing has one of two values. It can represent one option or the other, like a switch being off or on. A qubit is different because it is described by a quantum state. It can exist in a superposition of possible measurement outcomes, and when measured in a particular way, it produces one definite result according to quantum probabilities. This does not mean a qubit is simply both classical options in the lazy sense, as though it cannot make up its mind before breakfast. A qubit is not a confused bit. It is a genuinely quantum system whose state contains more structure than an ordinary bit. That structure can create interference, can be changed through quantum operations, and can become entangled with other qubits. Entanglement is where quantum information becomes especially powerful. If two qubits are entangled, the information in the pair is not simply stored separately in one qubit and then the other. Some of the most important information belongs to the relationship between them. The combined system has a state that cannot be reduced to independent states for each part. In that sense, quantum information changes the meaning of what it is to describe a particle at all. The particle is no longer only a little object with a private list of properties. It may be one part of a larger informational structure, where the whole carries facts that the individual pieces do not possess alone. This is why entanglement became more than a philosophical embarrassment left over from arguments between Einstein and Bohr. In quantum information science, entanglement became a resource. That change is one of the great shifts in modern physics. What once looked like a problem to be explained away became something scientists learned to use. Several figures helped build this new view. Richard Feynman argued that quantum systems might be best simulated by machines that themselves used quantum rules, because ordinary classical computers struggle to efficiently imitate many quantum systems. David Deutsch developed the idea of a universal quantum computer, showing that quantum computation could be understood as a general model of information processing. Charles Bennett and Gilles Brassard helped create quantum cryptography, including the famous Bennett-Brassard 1984 protocol, which showed how quantum states could help reveal eavesdropping. Peter Shaw later discovered a quantum algorithm for factoring large numbers efficiently in principle, showing that quantum computers could threaten some widely used forms of classical encryption if large enough reliable machines were built. These developments did not make entanglement less strange. They made its strangeness useful. In a classical computer, information is usually stored in bits that can be copied, checked, and moved around with great reliability. The physical object carrying the bit might be a voltage, a magnetic region, or a tiny transistor state. But the logic is essentially classical. A bit is one thing or the other. A classical computer can be astonishingly fast, but its information does not use superposition and entanglement in the same direct way. A quantum computer works differently. Its qubits can be placed into carefully prepared quantum states, allowed to interact, and then measured. Entanglement can link qubits into shared states whose behavior cannot be described as merely a collection of independent parts. Quantum algorithms try to use this structure, along with interference, to make certain calculations possible with fewer resources than the best-known classical methods. This does not mean quantum computers are magic machines that make every difficult problem easy. They're not enchanted laptops. They are specialized devices that may offer advantages for particular tasks, such as simulating quantum systems, certain optimization problems, secure communication protocols, or mathematical problems with the right structure. They're also extremely hard to build, because qubits are fragile and entanglement is easily damaged by noise and decoherence. Still, the conceptual point is enormous. Entanglement shows that information can be stored in relationships, not only in individual objects. This is why an entangled pair cannot be fully understood by asking only what each particle is doing separately. The pattern belongs to the pair. The relationship carries physical significance. That is also why quantum information is difficult. The same features that make it powerful make it delicate. A classical bit can often be copied and protected by simple redundancy. A qubit cannot be copied perfectly if its unknown state is arbitrary, because of the no-cloning theorem. Entangled states can be disturbed by unwanted measurement, environmental contact, or tiny errors. Preserving quantum information means protecting not just particles, but the fragile relationships between them. Once information itself is understood quantum mechanically, entanglement begins to allow protocols that sound impossible at first. One of the most famous is quantum teleportation. The name is dramatic and perhaps slightly guilty of borrowing a science fiction coat that does not quite fit. But the real process is even more interesting in a quieter way. It does not move matter from place to place. It transfers an unknown quantum state from one system to another, using shared entanglement and ordinary classical communication. That possibility only makes sense after the meaning of a particle has changed. A particle is not merely a tiny object travelling through space with a label attached. In quantum theory, what matters is its state, its possible measurement outcomes, and its relationship to other systems. Entanglement reveals that these relationships are not decorative extras. They can be central to what the physical situation actually is. The connection that once seemed like an embarrassment became a tool. The mystery became a resource. And the tiny particle, once imagined as a little object with its own private facts, became part of a deeper language of quantum information, where sometimes the most important thing is not the particle itself, but the pattern it shares with another. Quantum teleportation is real, which is a sentence that sounds as though it has wandered in from a more excitable kind of science program. The name is almost impossible to hear without imagining a person stepping into a glowing booth, disappearing in a shimmer of light and appearing somewhere else beside a mildly confused alien holding a clipboard. That is not what quantum teleportation means. It does not move a body through space. It does not transport memories, shoes, sandwiches, houseplants, or anyone's slightly panicked sense of dignity from one location to another. No object is broken apart and rebuilt elsewhere. What quantum teleportation transfers is an unknown quantum state, A quantum state is the full quantum description of a system. It tells physicists what can be predicted about possible measurement outcomes. If a particle is in a particular quantum state, that state may include information about properties such as polarization, spin, or another measurable feature, depending on the system being used. Quantum teleportation is a protocol for transferring that state from one physical system to another, using entanglement and ordinary classical communication. The theoretical basis for quantum teleportation was proposed in 1993 by Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters. Their idea showed that entanglement could be used not merely as a strange correlation, but as a practical tool for moving quantum information from one system to another. It was a remarkable shift. Entanglement, once treated as the awkward guest at the foundations of physics, had been handed a job. To understand why teleportation is needed at all, it helps to remember that quantum information is not like ordinary information. If someone has a written note, it can be copied. If a computer file is stored in one place, it can usually be duplicated somewhere else. Classical information is often robust enough to be checked, backed up, and sent around with great confidence, unless someone names the file final version, and then creates 7 more final versions, as nature never intended. An unknown quantum state cannot be copied perfectly in that simple way. This is because of the no-cloning theorem, which says that an arbitrary unknown quantum state cannot be perfectly duplicated. A qubit cannot be copied like a line of text or a photograph. If the state is unknown, there is no general operation that can produce an identical copy while leaving the original intact. So quantum teleportation does not copy the original state. It transfers it. The original quantum state is effectively destroyed in the process of being measured, while the same state can be reconstructed on a different system elsewhere. This detail matters enormously. Without it, teleportation would violate the no-cloning theorem by making a perfect duplicate. Quantum mechanics is strange, but it is not careless. It has rules, and it guards some of them very firmly. The process begins with entanglement. 2 parties, often called sender and receiver in simple explanations, must share an entangled pair of particles. One particle from the pair is kept by the sender, and the other is sent to the receiver. The sender also has another particle carrying the unknown quantum state that needs to be teleported. The sender performs a joint measurement on the unknown state, and they're half of the entangled pair. This measurement links the unknown state with the shared entanglement and produces a result. But that result by itself is not enough for the receiver to recover the teleported state. The sender must communicate the measurement result through an ordinary classical channel, such as a light signal, radio signal, or electronic message. Only after receiving that classical information can the receiver perform the correct operation on their particle. Then the receiver's particle takes on the original unknown quantum state. The state has been transferred, but not by sending matter through space and not by sending a faster-than-light signal. The classical message is essential, and it obeys the speed limit of relativity. This is the part that keeps quantum teleportation from becoming a cosmic shortcut. Entanglement provides the shared quantum relationship, but classical communication completes the process. Without the ordinary message, the receiver cannot know what operation to perform. The protocol cannot be used to send information instantly. It does not break causality. It does not allow someone to teleport a warning to the other side of the galaxy before light could arrive. Yet it still does something purely classical physics cannot do. It transfers an unknown quantum state using a shared entangled resource. That is why quantum teleportation became one of the clearest examples of entanglement as a tool. The entangled particles do not carry a message in the normal sense. They provide a structure that, when combined with measurement and classical communication, allows quantum information to be moved in a way that would be impossible if particles only behaved like classical objects. Experimental demonstrations soon followed the original proposal. Anton Zeilinger's group and other quantum optics laboratories helped show that quantum teleportation could be performed with photons. In these experiments, the states of photons were transferred using entanglement and carefully timed measurements. Later work extended teleportation over increasing distances and across different physical platforms, including photons, trapped ions, atoms, and solid-state systems. Each version had its own technical difficulties, but the underlying principle remained the same. These experiments are delicate because every part of the process must be controlled. The entangled pair must be created and preserved. The measurement must be performed correctly. The classical information must be transmitted. The receiving system must be adjusted in the right way. Noise, loss, imperfect detectors, and environmental disturbance can all spoil the result. Quantum teleportation is real, but it is not casual. It is not the sort of thing the universe does while half asleep. The wider meaning is even more important than the name. Quantum teleportation shows that entanglement does not send faster-than-light messages, yet it still enables tasks that ordinary classical physics cannot reproduce. The connection is not a telephone. It is not a tunnel for matter. It is not a mystical thread pulling one object instantly into another place. It is a shared quantum resource. That is what makes the idea so quietly astonishing. The impossible connection does not let scientists ignore the structure of spacetime. It does not overthrow Einstein's speed limit. Instead, it works within the rules, using entanglement, measurement, and communication together. The result sounds impossible only until each piece is unpacked. Quantum teleportation is real, but the thing being teleported is not an object. It is the quantum state of a system, transferred from one physical carrier to another. Nothing flashes across the room. No body dissolves into light. No science fiction machine hums in the corner. And yet, in a careful laboratory, with entanglement prepared and protected, information that cannot be copied can still be moved. That is stranger than the glowing booth. Security usually depends on keeping secrets hidden. A password must not be guessed. A private key must not be stolen. A message must not be read by the wrong person. In ordinary digital life, protection comes from mathematics, careful engineering, and the hope that nobody has chosen password 123 and then taped it to the side of a monitor. Modern encryption can be extremely strong, but it still belongs to the classical world of information. Bits are arranged, transformed, locked, sent, unlocked, and stored. Quantum cryptography asks a different kind of question. What if the physical rules of quantum mechanics could help protect information? What if eavesdropping did not merely become difficult, but could leave detectable traces because measurement itself changes a quantum system? One of the clearest practical ideas in this field is quantum key distribution. This does not mean every message becomes magically wrapped in quantum mist. It means two parties use quantum states to help create and share a secret key. That key can then be used with ordinary encryption methods to protect communication. The quantum part helps with the key, not with every single piece of the digital system around it. The most famous early protocol is the Bennett-Brassard 1984 protocol, known as BB84. It was proposed by Charles Bennett and Gilles Brassard, and it showed how quantum states could be used to reveal the presence of an eavesdropper. In a simple version, one party sends a sequence of quantum states, such as polarized photons, to another party. The receiver measures them using different possible measurement choices. Later, the two compare some information through an ordinary public channel, without revealing the final key itself. The security idea comes from the fact that unknown quantum states cannot be measured without consequences. If an eavesdropper intercepts the photons and tries to measure them, they may disturb the states. That disturbance can show up as errors when the sender and receiver compare part of their results. The message is not protected because photons are tiny and shy. It is protected because quantum measurement is not a passive act of peeking at a perfectly classical object. This is different from ordinary encryption. In classical cryptography, a message is often protected because solving the underlying mathematical problem would take too long with available computers. Quantum key distribution is not mainly about making a mathematical puzzle harder. It is about using the physical behavior of quantum systems to detect intrusion during the creation of a shared key. The key still has to be used carefully, stored securely, and combined with proper authentication. Quantum mechanics helps, but it does not politely fix every bad security habit in the building. Entanglement adds another version of the idea. In 1991, Arthur Eckert proposed an entanglement-based protocol known as E91. Instead of only sending prepared quantum states, this approach uses entangled pairs. Two distant users receive particles from entangled pairs and measure them. If the correlations violate a Bell inequality in the expected way, those results can help show that the shared data has genuine quantum features and has not been quietly replaced by a classical trick. This connects security to one of the deepest ideas in entanglement. Bell inequality violations show that the correlations between the particles are not explainable by simple local hidden instructions. In the right protocol, that non-classical behavior can become part of the security test. The same feature that once troubled Einstein becomes useful. The universe's refusal to behave like a set of sealed envelopes can help reveal whether someone has been tampering with the conversation. Real-world quantum communication has moved beyond tabletop experiments. Research groups and institutions have tested quantum key distribution through optical fibers, free space links, and satellite systems. The Chinese Academy of Sciences has played a major role in large-scale demonstrations, including the MISSIUS satellite. MISSIUS was used for satellite-based quantum communication experiments, including long-distance quantum key distribution and entanglement distribution. These achievements are impressive, but they should be described carefully. They are demonstrations of important capabilities, not proof that the entire internet has quietly become quantum secure while everyone was making tea. There are still major practical limitations. Distance is one of them. Photons can be lost in optical fiber, absorbed by the atmosphere, scattered or misdirected. Over long distances, signals weaken. Quantum repeaters are being researched as a possible way to extend quantum networks, but fully practical large-scale quantum repeater networks remain technically difficult. Hardware imperfections also matter. Real detectors are not perfect. Real photon sources can fail. Devices can have side channels, where information leaks through some unintended feature of the equipment. Detector vulnerabilities have been studied carefully because attackers do not always attack the elegant theory. Sometimes they attack the messy physical device sitting on the table, which is rude but effective. Trusted nodes are another limitation. Some long-distance quantum key distribution networks rely on intermediate stations that must be trusted. If those stations are compromised, the security of the whole system can be weakened. Cost and integration are also serious barriers. Quantum communication equipment must fit into existing networks, work reliably, and justify its complexity. A technology can be scientifically beautiful and still be inconveniently expensive, which is one of the universe's less poetic habits. Even so, quantum security remains one of the clearest examples of entanglement and quantum information becoming practical. It shows that quantum physics is not only a theory about strange particles in isolated experiments, it can change how information is created, shared, and protected. The important point is balance. Quantum cryptography is powerful but not magical. It does not replace all classical security. It does not make every system unhackable. It does not remove the need for careful engineering, authentication, software security, and human discipline. A quantum key cannot save a system if someone leaves the door open elsewhere, but it does reveal something remarkable. Entanglement is useful precisely because it is not just an ordinary hidden connection. It is a measurable non-classical relationship. The same strangeness that once made quantum physics seem almost impossible to interpret can become a tool for detecting interference and protecting information. The connection that should not exist, in the old classical sense, does not merely challenge intuition. Under careful conditions, it can help keep secrets. A quantum computer is not simply a faster version of an ordinary computer. That is one of the first things worth clearing away, because the phrase can easily invite the wrong picture. A quantum computer is not a magical laptop that opens spreadsheets at supernatural speed, makes every password vanish in fear, and calmly solves every difficult problem before the kettle has boiled. It is a different kind of machine, built to use quantum rules for certain kinds of information processing. An ordinary classical computer uses bits. Each bit is in one definite state at a time, representing one option or another. A quantum computer uses qubits, and a qubit is described by a quantum state. That state can involve superposition, where more than one possible measurement outcome is present in the mathematical description before measurement. Qubits can also interfere with one another, meaning different possible paths through a calculation can reinforce or cancel each other. And most importantly for this story, qubits can become entangled. Entanglement allows the state of several qubits to become a shared structure, not just a list of separate individual states. The information is partly held in the relationships among the qubits. This is where quantum computing begins to look genuinely different. A classical computer can certainly track relationships between bits, but it does so by storing and updating ordinary data. Entangled qubits can hold correlations that belong to the combined quantum state itself. The machine is not merely calculating about quantum relationships, it is using them. Richard Feynman helped make this idea feel unavoidable. In the early 1980s, he argued that nature is quantum mechanical, so trying to simulate quantum systems with ordinary classical computers may become overwhelmingly inefficient. If the system being studied is quantum, perhaps the best machine to simulate it should also be quantum. This was a beautifully simple insight with enormous consequences. Instead of forcing a classical machine to imitate the quantum world from the outside, build a machine that follows quantum rules from within. David Deutsch later developed the concept of a universal quantum computer. He showed that quantum computation could be treated as a general model of information processing, not just a special trick for one type of physics simulation. This helped turn quantum computing into a serious theoretical field. The question was no longer only whether quantum systems were strange, it was whether their strangeness could be organized into computation. Then came quantum algorithms. Peter Shor developed a famous algorithm showing that a sufficiently powerful and reliable quantum computer could factor large numbers far more efficiently than the best-known classical methods. This mattered because some widely used forms of encryption depend on the difficulty of factoring large numbers. Lovegrover developed a quantum search algorithm that can speed up certain kinds of unstructured search problems. These discoveries showed that quantum computers were not just philosophical toys. They could, at least in principle, change what kinds of calculations are practical. But the phrase, at least in principle, is doing a great deal of work there. Quantum computers do not make every problem easy. They are not universal shortcuts around difficulty. Many tasks would not benefit much from quantum computation. Some would be better handled by ordinary classical computers, which are reliable, mature, cheap by comparison, and much less likely to throw a delicate tantrum because the surrounding environment got slightly involved. The power of quantum computing comes from using superposition, interference, and entanglement in carefully designed ways. Superposition allows qubits to be described by combinations of possible states. Interference allows some computational paths to strengthen, while others cancel. Entanglement links qubits into shared states, allowing algorithms to explore certain structures that classical bits cannot directly mimic. The trick is not that the computer simply tries every answer at once and picks the right one, which is a common but misleading shortcut. The trick is that the quantum state evolves so that, when measured, useful answers become more likely and unhelpful possibilities are suppressed. Entanglement is central because many interesting quantum computations require correlations spread across multiple qubits. The system's behavior cannot be fully understood by looking at each qubit separately. The combined state matters. In that sense, the same feature that once made Einstein uneasy becomes part of the machinery. The connection that seemed like a threat to classical separability becomes something engineers try to create, control, and protect. Protecting it is the hard part. Qubits are fragile. They are easily disturbed by heat, vibration, stray electromagnetic fields, imperfect materials, and unwanted interaction with the environment. These disturbances create noise, and noise causes errors. In a classical computer, errors can often be corrected by copying information and checking it repeatedly. Quantum information is harder because unknown quantum states cannot be copied perfectly. The no-cloning theorem refuses to let quantum information behave like an ordinary file. Quantum error correction offers a way through this difficulty. It spreads quantum information across several physical qubits so that errors can be detected and corrected without directly measuring and destroying the protected quantum state. Peter Shor also made an early major contribution here with his quantum error correcting code. This was crucial because large useful quantum computers will need not merely qubits, but reliable logical qubits built from many error-prone physical qubits. The challenge is not only to create entanglement, but to keep it alive while computation happens. Different research groups pursue this goal with different physical systems. Superconducting qubits use circuits cooled to extremely low temperatures and are studied by groups such as Google, Quantum AI, IBM Quantum, and many academic laboratories. Trapped ion systems use charged atoms held in electromagnetic fields and manipulated with lasers, with companies such as Quantinuum and IonQ helping develop the technology. Neutral atom quantum computers arrange uncharged atoms using laser light, while photonic quantum computing uses particles of light as carriers of quantum information. Each approach has strengths and weaknesses. Superconducting qubits can be built with techniques related to advanced chip fabrication, but they are sensitive to noise and require extreme cooling. Trapped ions can have very high precision, but scaling them into larger machines is difficult. Neutral atoms offer promising arrays of many particles, while photons are excellent for communication, but challenging for certain kinds of interaction. There is no single obvious winner yet. The field is still a careful race between physics, engineering, patience, and an impressive number of cables. What matters for entanglement is that all these approaches depend on controlling quantum relationships. A quantum computer is not powerful because each qubit is impressive by itself. A lone qubit is interesting, but the deeper power appears when many qubits are linked, manipulated, and measured in ways that preserve useful quantum structure. The computation lives in the pattern. This brings the story back to the strange connection at the heart of quantum mechanics. Entanglement once seemed like a problem, a sign that quantum theory was refusing to respect the old boundaries between separate objects. In quantum computing, that same feature becomes a tool. Scientists try to engineer it on chips, hold it inside vacuum chambers, guide it through photons, protect it with error correction, and scale it into larger systems. The connection that should not exist has become something researchers attempt to build deliberately. It is still fragile. It is still difficult. It still resists every lazy comparison to ordinary machines. But it is no longer only an argument about what reality means, it is hardware. Entanglement is easiest to picture when the story begins with two particles. Two photons fly away from a crystal. Two electrons share a linked spin state. Two atoms are prepared so that measuring one helps predict what will be found in the other. These examples are clean, elegant, and useful, which is why they appear so often. They give the mind something small enough to hold. One particle here, one particle there, and between them a relationship that does not behave like an ordinary connection. But entanglement is not only a two-particle trick. The same underlying principle can appear in larger collections of quantum systems. Photons, electrons, atoms, and qubits are the most famous characters in the story, but the deeper idea reaches further. Quantum mechanics does not stop being quantum when more particles enter the room. It becomes harder to calculate, harder to visualize, and much more difficult to keep tidy, but the rules still apply. In fact, many of the most important materials and phases of matter in modern physics depend on collective quantum behavior. This is the world of many-body quantum physics. A many-body quantum system contains a large number of interacting particles, often so many that treating each one as a completely independent object becomes hopeless. In classical physics, a large system may be complicated because it contains many moving pieces. A gas, for example, contains an enormous number of molecules, but each molecule can still be imagined as having its own position and motion. The difficulty is mainly practical. There are simply too many details to track. In many-body quantum physics, the difficulty can be deeper. The particles may share a collective quantum state. Their behavior may depend not only on what each particle is doing separately, but on the structure of the whole. Entanglement can spread through the system, linking parts of it in patterns that cannot be reduced to little private stories for each particle. The whole does not merely contain the parts. At the quantum level, the whole can help define what the parts are allowed to do. This idea becomes especially important in condensed matter physics, the study of solids, liquids, and complex materials. Condensed matter physics may sound less dramatic than black holes or cosmic explosions, but it is one of the richest areas of modern science. It explains why materials conduct electricity, why magnets behave as they do, why crystals have structure, why some substances become superconductors, and why collective behavior can produce properties that no single particle possesses by itself. A key idea here is the quantum phase of matter. A phase is a distinct form matter can take, such as solid, liquid, or gas. But quantum physics adds stranger possibilities. Some phases are defined not only by ordinary arrangement or temperature, but by deep quantum order. Superconductivity is one example. In a superconductor, electrical resistance vanishes under the right conditions, allowing electric current to flow without the usual energy loss. This is not because one electron suddenly becomes extremely determined, it is a collective quantum phenomenon. The most famous microscopic explanation of conventional superconductivity is the BCS theory, named after John Bardeen, Leon Cooper, and Robert Schrieffer. In this theory, electrons can form linked pairs known as Cooper pairs through interactions with the vibrating structure of the material. These pairs then move through the material in a coordinated quantum state. The result is not simply many separate electrons travelling more politely than usual, it is a shared quantum order across the material. Superfluidity offers another striking example. A superfluid can flow with no ordinary viscosity, allowing it to behave in ways that seem almost impossible from everyday experience. Liquid helium, when cooled to extremely low temperatures, can enter a superfluid state. Anthony Leggett made major contributions to understanding superfluidity and macroscopic quantum systems, helping clarify how quantum behavior can appear across larger scales. Again, the essential point is not that one atom performs a clever solo act. It is that many atoms enter a shared quantum state whose collective behavior is unlike anything in ordinary fluid motion. Magnetism also has deep quantum roots. In a magnet, the tiny magnetic properties of many particles align or organize in a collective pattern. Classical pictures can describe some broad features, but the real explanation depends on quantum spin, exchange interactions, and the ways particles influence one another through the quantum rules of matter. Lev Landau, one of the great figures in 20th century theoretical physics, developed powerful ideas about phase transitions and condensed matter theory. His work helped physicists understand how large systems can change from one kind of order to another, often through principles that reach far beyond the behavior of individual particles. Entanglement is increasingly understood as part of this wider story. In simple two-particle examples, Entanglement means that the state of the pair cannot be separated into two independent descriptions. In many body systems, something similar can happen across larger regions. One part of a material may be deeply linked with another part through the structure of the shared quantum state. The pattern can be subtle. It may not look like two particles producing dramatic correlations in a Bell test. Instead, it may appear as a hidden organizing principle behind the material's behavior. Physicists use the idea of entanglement entropy to describe how strongly parts of a quantum system are linked. The word entropy can sound intimidating, because physics has a generous habit of using familiar words until they become slightly less familiar. Here, entanglement entropy is a way of asking how much quantum connection exists between one part of a system and the rest. If a region can be described almost independently, the entanglement is low. If the region's description is deeply tied to the larger whole, the entanglement is higher. This is not merely philosophical. Entanglement entropy helps physicists classify quantum phases of matter, study quantum phase transitions, and understand why some systems are easy or difficult to simulate. It gives a way of measuring the hidden connectedness inside quantum matter. One of the practical tools that grew from this insight is the use of tensor networks. A tensor network is a mathematical method for representing complicated quantum states by focusing on their entanglement structure. Instead of trying to write down every impossible detail of a huge quantum system directly, physicists represent the system through connected mathematical pieces. This can make certain many-body problems more manageable. Stephen White's density matrix renormalization group became one of the most important methods for studying strongly interacting quantum systems, especially in one-dimensional systems. It works so well in many cases because it captures the relevant entanglement efficiently. Later, tensor network methods expanded this way of thinking further. Entanglement, once a strange philosophical problem, became a guide for calculation. The mystery had become useful again. This is one of the quiet revolutions in modern physics. Entanglement is not only something seen when two particles fly apart and confuse everyone in a very precise way. It is also a structural feature of quantum matter. It helps explain how large groups of particles can act together, how new phases emerge, and how physicists can study systems too complex for simple, particle-by-particle thinking. The connection that should not exist, according to old classical intuition, is not confined to tiny laboratory pairs. It can spread through materials, organize collective behavior, and shape the hidden architecture of matter itself. Quantum connectedness is not a decorative oddity sitting at the edge of physics. It is one of the deep organizing ideas running through the field. Sometimes it appears as two photons linked across space. Sometimes it appears as a superconductor carrying current without resistance. Sometimes it appears in the mathematics that let scientists understand complex materials. The strangest connection in the universe is not always dramatic. Sometimes it is quietly holding the behavior of matter together. The everyday world does not look especially quantum. A table appears to stay where it is. A cup of tea does not seem to hover between being on the desk and on the floor, unless someone has placed it very badly. A cat walks through a room as one definite animal, not as a visible superposition of every possible feline decision. The world of ordinary experience seems solid, stable, and classical. Objects have locations. Events happen in order. Things do not obviously behave as though they are delicately entangled with everything around them, and yet, underneath that ordinary stability, the same quantum rules still apply. Atoms are quantum systems. Electrons are quantum systems. The bonds that hold molecules together depend on quantum mechanics. The structure of matter, the chemistry of life, the behavior of light, and the stability of solids all come from quantum principles. The world does not stop being quantum just because it becomes large enough to trip over. The question is why the quantum strangeness becomes so well hidden. The answer begins with decoherence. Environmental decoherence is the process by which a quantum system loses its visible quantum interference. because it becomes entangled with its surroundings. A small, isolated system, such as an electron, photon, ion, or carefully prepared qubit, can preserve delicate relationships within its quantum state. But ordinary objects are not isolated. They are constantly interacting with air molecules, heat, light, vibrations, nearby surfaces, electromagnetic fields, and countless microscopic disturbances. Every one of those interactions carries away a little information. A photon reflects from a surface. An air molecule bounces off an object. Heat radiation leaks into the room. Tiny vibrations pass through a table. None of these events needs to be dramatic. There does not need to be a scientist with a clipboard making an official measurement. The environment itself becomes involved. It becomes, in a physical sense, a vast witness. This does not mean the environment is conscious. It does not mean the air is thoughtfully observing the universe and writing down results in very small handwriting. It means that physical interaction spreads quantum information outward. The system becomes entangled with its surroundings in an uncontrolled way. Once that happens, the delicate phase relationships that allow superposition and interference become effectively inaccessible to ordinary observation. That phrase matters. Effectively inaccessible. Decoherence does not mean quantum mechanics stops working. It does not mean a quantum system suddenly becomes classical because it has crossed some invisible size limit and been issued a sensible hat. The underlying physics remains quantum. But the patterns that would reveal clean superposition or interference become dispersed into an enormous environment. To recover them, one would need to track and reverse the states of a fantastically large number of surrounding particles and fields. For everyday objects, that is not merely difficult. It is practically hopeless. This is why a dust grain, a warm cup, or a living creature does not visibly behave like an isolated electron. The object is constantly interacting with its environment. Its quantum information is not neatly stored in one protected place. It is leaking into the surrounding world through countless tiny channels. The result is a stable, classical appearance. The object seems to have a definite position and definite properties, not because quantum rules have disappeared, but because the quantum alternatives can no longer interfere in any observable way. Wojciech Zurek has played an important role in developing this picture. His work on pointer states and quantum Darwinism explores how certain stable classical features can emerge from quantum systems interacting with their environments. Pointer states are the states that remain relatively robust under environmental interaction. They are the kinds of states that can survive being repeatedly monitored by the surroundings without dissolving into visible quantum ambiguity. Quantum Darwinism extends this idea by suggesting that the environment does more than merely destroy interference. It also spreads multiple copies of information about certain stable states into the surroundings. Many observers can then access the same classical-looking facts indirectly by intercepting fragments of the environment such as reflected light. This helps explain why the ordinary world appears objective. Several people can look at the same chair and agree that it is there, rather than each needing direct access to the chair's full quantum state. This is one approach to the quantum-to-classical transition, the problem of explaining how the familiar classical world emerges from quantum laws. It does not necessarily answer every philosophical question about measurement, but it provides a powerful physical account of why everyday reality looks so stable. The classical world is not separate from the quantum world. It is what quantum behavior looks like after immense environmental entanglement has hidden the fragile interference patterns from view. Laboratory entanglement is so difficult for exactly this reason. To preserve a clean quantum state, scientists must protect it from the environment. A superconducting qubit may need to be cooled to temperatures close to absolute zero, where thermal motion is drastically reduced. Trapped ions may be held in ultra-high vacuum and manipulated with lasers. Photons may be guided through carefully designed optical systems. Atoms may be cooled and isolated so their quantum states last long enough to study. Everyday objects live at the opposite extreme. They are warm, exposed, constantly illuminated, surrounded by air, and connected to the rest of the world through trillions upon trillions of microscopic interactions. A single laboratory qubit might be shielded from stray electromagnetic noise and cooled inside a specialized machine. A teacup on a kitchen table is being touched by air molecules, warmed by the room, struck by light, vibrated by footsteps, and gravitationally connected to everything nearby. It is not a quiet place to keep a quantum secret. This is why large, warm objects are extremely difficult to place into clean, useful, entangled states. They are not too large for quantum mechanics in principle, rather they're too entangled with everything else in practice. Their quantum relationships spread into the environment almost instantly. The delicate state becomes part of a vast, tangled web that cannot be controlled. The boundary between quantum and everyday reality is therefore not a hard wall. It is a fragile transition shaped by isolation, temperature, complexity, and environmental contact. The smaller, colder, and better protected a system is, the easier it becomes to observe quantum behavior. The larger, warmer, and more exposed it is, the more classical it appears. This matters far beyond laboratory technology. Decoherence helps explain why the familiar world has definite features, while entanglement hints that separateness itself may not be as fundamental as it seems. The same idea that links particles, powers quantum information, and shapes materials may also reach into deeper questions about spacetime and gravity. If entanglement can help explain how ordinary matter behaves, perhaps it also has something to say about the structure of the universe itself. The fragile boundary between quantum possibility and everyday fact may not be the end of the story. It may be the doorway into an even deeper question, whether spacetime, gravity, and the large-scale fabric of reality are also connected to the hidden architecture of quantum information. Entanglement began as a puzzle about particles, but it did not stay there. Over time, physicists began to notice that the same strange idea might have something to say about black holes, quantum gravity, and even the structure of space itself. That may sound like a very large leap. One moment there are photons in a laboratory, and the next there are black holes, horizons, and the fabric of the universe, which is quite a lot for one scientific concept to be getting on with. But in modern physics, entanglement has become one of the bridges between the smallest and the largest questions nature allows. The reason is information. In ordinary life, black holes are often imagined as cosmic drains, regions where matter falls in and nothing escapes. General relativity, Albert Einstein's theory of gravity, describes a black hole as a region of space-time where gravity is so strong that beyond a boundary called the event horizon, not even light can return. In the classical picture, whatever crosses that horizon is hidden from the outside universe. Then quantum theory made the situation stranger. Jacob Bekenstein argued that black holes should have entropy, meaning they possess a measure of hidden information or microscopic disorder. This was a radical idea because entropy usually belongs to physical systems with internal structure, such as gases, liquids, or hot objects made of many particles. A black hole, in the simple classical description, seemed almost featureless. It could be described by properties such as mass, charge, and rotation, but not by the detailed identity of everything that had fallen inside. Stephen Hawking then showed that when quantum field theory is considered near the event horizon, black holes should not be completely black. They should emit a faint thermal radiation, now called Hawking radiation. Over immense timescales, this radiation means a black hole can slowly lose energy and eventually evaporate. For large astrophysical black holes, the process is fantastically slow, far longer than the current age of the universe. But conceptually, it changed everything. The problem is that Hawking radiation appears thermal, meaning it looks as though it carries no detailed memory of what formed the black hole. If a black hole forms from matter carrying information and then later evaporates into radiation, that seems to have lost that information, quantum theory is in trouble. Quantum mechanics normally preserves information in the full evolution of a closed system. It does not allow the detailed state of the universe simply to be erased. This tension is called the black hole information paradox. The paradox asks what happens to information when matter falls into a black hole and the black hole later evaporates. Does the information disappear, violating quantum theory? Is it somehow encoded in the Hawking radiation? Does it remain hidden in a remnant? Or does the classical picture of spacetime itself need to change? No simple answer has been universally accepted, but the paradox forced physicists to take information seriously in gravitational physics. Black holes became not only objects of gravity, but laboratories for the deepest conflict between quantum mechanics and spacetime. One idea that grew from this struggle is the holographic principle, associated especially with Gerard 't Hooft and Leonard Susskind. The holographic principle suggests that, in certain theories of quantum gravity, the information contained in a region of space may be related to the boundary of that region rather than only to its volume. This is not the same as saying the universe is a literal hologram projected for dramatic effect. It is a precise theoretical idea about how information may be counted and represented when gravity and quantum theory are brought together. The most famous framework where this idea becomes mathematically powerful is the anti-de Sitter conformal field theory correspondence, proposed by Juan Maldacena. This correspondence links a theory of gravity in a certain kind of spacetime with a quantum field theory defined on its boundary. In this framework, spacetime geometry and quantum information are deeply connected. Entanglement in the boundary theory can be related to geometric features in the gravitational description. This is one of the most remarkable shifts in modern theoretical physics. Entanglement is no longer only something that happens inside space between particles. In certain models, patterns of entanglement may help build the appearance of space. The geometry of a gravitational world can be linked to the quantum relationships in a theory without gravity. Space, in this view, begins to look less like a simple stage on which physics happens, and more like something that may emerge from deeper quantum structure. There is another famous and more speculative idea that connects entanglement with spacetime. In general relativity, an Einstein-Rosen bridge is a theoretical bridge between regions of spacetime, often loosely associated with the idea of a wormhole. Separately, the Einstein Podolsky Rosen argument concerns entangled quantum systems. Juan Maldacena and Leonard Susskind proposed the idea known as ER equals EPR, suggesting a deep connection between certain kinds of entanglement and certain kinds of wormhole geometry. This proposal must be handled carefully. It does not mean ordinary entangled particles create usable tunnels through space. It does not mean two entangled photons are connected by a wormhole that could carry a message, a spacecraft, or a very determined postcard. It is a theoretical proposal about the relationship between quantum entanglement and space-time geometry in particular contexts. It is not a settled fact about every entangled system in the universe. Still, the suggestion is extraordinary. Einstein's own work produced both pieces of the phrase, Einstein-Rosen bridges from general relativity, and the Einstein Podolsky Rosen argument from quantum foundations. Decades later, physicists began asking whether those two strange ideas, one about space-time and one about entanglement, might not be entirely separate after all. This does not solve quantum gravity. It does not give a complete final theory of space-time, but it shows how far entanglement has travelled. A concept that once looked like an embarrassment in the interpretation of quantum mechanics has become central to some of the deepest attempts to understand black holes, information, and the possible emergence of space. The connection that should not exist began by challenging the idea that particles are fully separate. Now, in some areas of modern theoretical physics, it hints at something even more unsettling. Perhaps certain descriptions of space itself depend on quantum connections underneath. Entanglement may not merely live within the fabric of space. In the most ambitious ideas now being explored, it may help explain how parts of that fabric hold together. Entanglement is no longer an experimental question in the simple sense. Physicists may still argue about what it means, but they do not seriously argue that the phenomenon itself is imaginary. Bell test experiments, entangled photons, trapped ions, superconducting qubits, quantum teleportation, and quantum information science have all made entanglement part of working physics. It is not a poetic metaphor, not a philosophical ornament, and not a piece of mathematical fog that vanishes when the instruments are switched on. The strange part is that agreement on the experiments has not produced agreement on the underlying picture. Quantum mechanics tells physicists how to calculate probabilities with extraordinary success. It tells them what patterns to expect when entangled particles are measured. It tells them how to prepare states, control systems, and compare results. But when the question becomes what is really happening beneath measurement, the answer depends on the interpretation of quantum mechanics being used. An interpretation is not usually a different set of laboratory predictions. Most major interpretations agree on the ordinary experimental results. The difference lies in what the mathematics is taken to mean. Does the wave function describe reality itself, or only knowledge about reality? Does it collapse when a measurement happens, or does it continue evolving? Are outcomes created, selected, branched, guided, or related to observers in a deeper way? Quantum physics is precise, but the story behind its precision remains unsettled. The Copenhagen interpretation is the most historically famous approach. It is associated with Niels Bohr and Werner Heisenberg, though it is not a single rigid doctrine with every detail carved neatly into stone. Broadly, it emphasizes measurement outcomes, experimental arrangements, and the limits of classical description. In this view, quantum mechanics does not always allow physicists to speak meaningfully about definite properties before measurement in the same way classical physics did. The setup matters. The question asked of nature matters. A particle's behavior cannot be separated cleanly from the conditions under which it is observed. For entanglement, this means the shared quantum state is not treated as a simple, hidden set of classical facts waiting to be revealed. The measurement context becomes part of what can be said. Bohr did not think quantum mechanics was incomplete in Einstein's sense. He thought Einstein was trying to preserve a kind of classical picture that nature had already refused to provide. Hugh Everett offered a very different idea with the many worlds interpretation. In this view, the wave function does not collapse. Instead, all possible outcomes continue as parts of a larger branching universal wave function. When a quantum measurement happens, the observer becomes entangled with the system, and different outcomes correspond to different branches. This avoids the problem of explaining a sudden collapse, but it replaces it with a vast and difficult picture of reality, where every possible quantum outcome is physically represented in some branch. Many worlds can sound extravagant, as if the universe is taken up overproduction as a hobby. But its appeal is that it treats the wave function, as always obeying the same quantum laws. There is no special moment when collapse must be added by hand. Entanglement becomes not just a connection between particles, but a process by which observers, measuring devices and environments become part of branching quantum structure. David Bohm's pilot wave theory, also called de Broglie-Bohm theory, takes another route. It is deterministic, meaning that the outcomes are fixed by the deeper state of the system. In this interpretation, particles have definite positions, but they are guided by a quantum wave. The theory is explicitly non-local, meaning that the guiding structure can link distant systems in a way that does not fit ordinary classical locality. This makes Bohm's theory attractive to those who want particles to have definite properties, but it comes with a cost. It preserves a kind of realism, yet gives up strict locality. Entangled particles are not mysterious because they lack definite positions. They are mysterious because the guiding quantum wave connects the behavior of separated systems in a non-local way. Objective collapse theories make a different choice. These theories propose that collapse is not merely an update in knowledge or a matter of interpretation, but a real physical process. The theory associated with Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber modifies quantum mechanics so that superpositions collapse spontaneously under certain conditions. Roger Penrose has also suggested that gravity may play a role in the collapse of quantum states, though this remains speculative and not part of settled physics. The appeal of objective collapse theories is that they try to explain why definite outcomes occur. They do not simply say the wave function appears to collapse when measured. They propose that collapse actually happens. The challenge is that such theories must make predictions that remain consistent with experiments while adding a real physical mechanism that has not yet been conclusively confirmed. Other interpretations shift the focus again. Relational quantum mechanics, associated with Carlo Rovelli, suggest that the properties of a system are not absolute in isolation, but are defined relative to other systems. A measurement does not reveal a single observer-independent fact in the old classical sense. It establishes facts in relation to the system that interacts with it. Quantum Bayesianism, associated with Christopher Fuchs, Rudiger Schack, and Carlton Caves, treats the quantum state as an expression of an observer's personal expectations about possible experiences, rather than as a direct physical object existing independently in the world. This does not make quantum mechanics casual or subjective in the everyday sense. It is still mathematically disciplined. But it changes what the wave function is understood to represent. These interpretations can feel like a menu in a restaurant where every option is brilliant, unsettling, and somehow missing the chips. Copenhagen gives up some classical realism. Many Worlds gives up a single outcome as the whole story. Bohm keeps definite particles, but accepts non-local guidance. Objective collapse modifies the dynamics. Relational quantum mechanics makes properties depend on relations. Quantum Bayesianism treats the quantum state as tied to an agent's expectations. Entanglement is difficult because it does not let every old intuition survive. Something must give. The classical picture wanted separate objects, definite properties, local influences, and one simple observer-independent story of what exists before measurement. Quantum mechanics does not hand all of that back. The connection that should not exist is not impossible because experiments reject it. Experiments confirm it. It is impossible only under the old assumptions about what a connection should be. Entanglement forces physics to choose which part of ordinary common sense must be loosened, and that may be why it remains so powerful. It does not merely show that particles can be strangely linked. It shows that reality may not be built from the kind of separate settled pieces the human mind expected to find. Quantum entanglement is the connection that should not exist, at least if the universe is judged by classical intuition. In the older picture, objects are separate things. They carry their own properties through space. They may influence one another, but only through contact, forces, fields, or signals that travel between them. A cause begins somewhere, moves through the world in some traceable way, and produces an effect somewhere else. This is the universe of everyday sense. It is the universe where distance matters, where messages take time, and where objects are expected to possess their own facts, whether anyone is looking or not. Entanglement does not fit that picture. It does not fit because quantum theory and repeated experiment both show that separated systems can share a state in a way that cannot be reduced to ordinary hidden information. Two particles can be linked so that the best description belongs to the pair, not to each particle separately. Measurements performed far apart can show correlations stronger than classical local hidden instructions should allow. The connection appears impossible only because the older assumptions about separateness were too simple. That is the quiet lesson running through the whole story. Entanglement is not an invitation to throw physics away. It is not evidence that the universe is lawless, mystical, or casually breaking its own rules whenever nobody is supervising. It is almost the opposite. Entanglement obeys rules with extraordinary precision. It appears in equations, laboratories, technologies, and experiments so carefully designed that even the loopholes have loopholes looking nervously over their shoulders. The strange part is that the rules are not the ones everyday intuition expected. Classical physics was built on powerful ideas. Locality said that objects should be influenced only by their surroundings, or by signals that travel through space at limited speed. Realism said that physical properties should have definite values before measurement, at least in the old familiar sense. Causality kept events in order, with causes coming before effects. Together, these ideas created a deeply satisfying picture of a universe, made from separate things interacting through understandable channels. Quantum mechanics did not erase that picture from ordinary life. Apples still fall, planets still orbit. Light still takes time to cross space. A cup left on a table does not dissolve into a poetic blur of possible crockery. But at very small scales, the deeper description changed. A quantum state does not always behave like a list of fixed properties. It gives probabilities for measurement outcomes. It can contain superposition. It can describe more than one system as a single shared whole. That shift began long before entanglement became famous. Classical physics cracked under the pressure of black body radiation, the ultraviolet catastrophe, the photoelectric effect, atomic spectra, and the strange wave-like behavior of matter. Max Planck's quantum hypothesis, Albert Einstein's photon, Niels Bohr's energy levels, Louis de Broglie's matter waves, Erwin Schrödinger's wave equation, Werner Heisenberg's matrix mechanics, and Max Born's probability interpretation all helped build a world in which particles were not simply tiny classical objects. Then the Einstein Podolsky Rosen argument brought the problem into sharp focus. Albert Einstein, Boris Podolsky, and Nathan Rosen argued that quantum mechanics must be incomplete if it allowed separated systems to be linked in this strange way. Einstein's discomfort was not stubbornness. It was a serious concern about locality, realism, and the meaning of a complete physical theory. If measurement of one system seemed to determine something about another distant system, then either the distant system already had that property, or quantum mechanics seemed to imply a troubling non-local connection. Schrödinger gave the mystery its name, entanglement. He understood that this was not a minor technical oddity. It was one of the defining features of quantum mechanics. It showed that the whole could not always be reduced to its parts. A pair of entangled particles was not like a pair of gloves hidden in separate boxes, where opening one box merely reveals what had already been true. The comparison is useful only until it fails, and it fails exactly where quantum physics becomes most interesting. John Bell then transformed the debate. Bell's theorem showed that the question could be tested. If local hidden variable theories were correct, separated measurements should obey certain limits called Bell inequalities. Quantum mechanics predicted that entangled systems could violate those limits. Later experiments by John Clauser, Stuart Friedman, Alain Aspect, Anton Zeilinger, and many others showed that nature follows the quantum predictions. Modern loophole-reduced Bell tests have made it far harder to dismiss entanglement as bad measurement, bad philosophy, or a misunderstanding hiding in the language. And yet entanglement still does not allow faster-than-light messaging. That is crucial. The no-communication theorem explains why individual measurement outcomes cannot be controlled to send chosen information. The correlations become clear only when observers later compare their results through ordinary classical communication, which still obeys the speed of light limit from Einstein's special relativity. Entanglement challenges separability, but it does not break causality. It unsettles the old picture while leaving the deep structure of cause and effect intact. This is why entanglement is so unusual. It does not behave like a signal, but it cannot be reduced to ordinary ignorance. It is not communication, yet it is not mere coincidence. It is a non-classical relationship written into the quantum state. That relationship now reaches far beyond the original philosophical debate. In laboratories, scientists create entangled photons, trapped ions, atoms, superconducting qubits, and other controlled quantum systems. In quantum information science, entanglement has become a resource. It helps make quantum teleportation possible, though not in the science fiction sense. It supports quantum key distribution and ideas about secure communication. It lies at the heart of quantum computing, where qubits, superposition, interference, and entanglement are used to process certain problems in ways classical bits cannot directly imitate. It also appears in many-body quantum physics. Entanglement helps physicists understand condensed matter systems, quantum phases, superconductivity, superfluidity, magnetism, tensor networks, and entanglement entropy. The strange connection is not only a dramatic pairing of two particles across space, it is part of the hidden structure of complex quantum matter. Even black holes have drawn entanglement into the deepest questions of modern theory. Jacob Bekenstein, Stephen Hawking, Gerard 't Hooft, Leonard Susskind, Juan Maldacena, and others helped reveal that information, entropy, gravity, and space-time may be connected in ways that classical physics never anticipated. In certain theoretical frameworks, entanglement may not merely exist within space. It may help explain how some descriptions of space itself hold together. The deepest lesson may be the failure of separability. Classical intuition expects the world to be built from independent parts, each carrying its own definite properties. Entanglement suggests that this is not always the most complete way to describe reality. Sometimes the relationship between parts is not secondary. Sometimes it is part of the primary physical description. The whole can be more fundamental than the separate stories of the pieces. That does not make reality unreal. It makes reality less straightforward than expected. The ordinary world remains stable because decoherence hides delicate quantum relationships from everyday view. Warm objects constantly interact with their surroundings, spreading quantum information into the environment. This is why tables, planets, cats, and people do not visibly behave like clean entangled particles in a laboratory. The quantum world is not absent. It is deeply buried beneath the classical appearance produced by enormous environmental complexity. Entanglement is therefore not a loophole in reality. It is not a place where the universe forgets its own rules. It is one of the clearest hints that the rules are deeper than the ones human intuition first imagined. The universe is not built only from separate pieces bumping into one another across empty space. At the quantum level, relationships can be woven into the description itself. The connection that should not exist does exist. It has been argued over, named, tested, engineered, protected, and used. It remains experimentally solid and philosophically unsettling, which is a rare combination. It shows that nature can be reliable without being intuitive, precise without being comfortable, and deeply ordered without looking like the old mechanical dream. Entanglement does not make the universe less real. It reveals that reality was never quite as separable as it seemed. Quantum entanglement is the connection that should not exist, at least under the old classical picture of the universe. In that older view, reality was made from independent things carrying their own settled properties through space. Objects could touch, collide, attract, repel, exchange energy, or send signals. Causes had paths, influences had journeys. A thing over here could affect a thing over there only if something crossed the distance between them. It was a powerful and deeply successful way to understand nature, and for the ordinary world of planets, falling objects, machines, and moving light, it still works beautifully. But entanglement shows that this picture is not complete. Two quantum systems can share one combined state, so that the most complete description belongs to the whole, rather than to each part separately. When those systems are measured, their results can reveal correlations too strong to be explained by simple hidden instructions carried from the beginning. This is why entanglement feels so strange. It behaves like a connection, yet not like any ordinary connection built from messages, forces, or contact. It should not exist if the universe is made only from separate pieces with fully independent facts. and yet it does exist, as one of the most tested features of quantum physics. The path to that realization began with the cracks in classical physics. Max Planck's quantum hypothesis revealed that energy exchange could come in discrete amounts. Albert Einstein's photon showed that light could behave as though it arrived in packets. Niels Bohr's atom introduced allowed energy levels. Erwin Schrödinger's wave function, Werner Heisenberg's matrix mechanics, and Max Born's probability interpretation helped build a theory where particles, waves, measurement, and possibility no longer fit ordinary categories. Then came the Einstein Podolsky Rosen argument, where Albert Einstein, Boris Podolsky, and Nathan Rosen tried to show that quantum mechanics must be incomplete. Schrödinger gave the mystery its name, entanglement. John Bell later transformed the debate by showing that the question could be tested. Bell's theorem drew a line between quantum predictions and local hidden variable theories. Experiments by John Clauser, Stuart Friedman, Alan Aspect, Anton Zeilinger, and later loophole-reduced Bell tests showed that nature follows the quantum prediction. The strange connection was not merely a philosophical mistake. It was measurable. And still, entanglement is not faster than light messaging. It is not supernatural influence. It is not proof that anything can affect anything else at will. Individual measurement results remain uncontrollable, and useful information still requires ordinary communication that obeys the speed limit of relativity. Entanglement gives correlation, not a cosmic telephone. The universe permits the pattern, but refuses to let it become an instant message. That is part of what makes it so remarkable. Entanglement does not break physics. It reveals that physics is subtler than the assumptions built from everyday experience. The same strange relationship now appears across modern science. Quantum teleportation uses entanglement and classical communication to transfer an unknown quantum state without copying it. Quantum cryptography uses quantum states and, in some protocols, entanglement to help detect eavesdropping. Quantum computers try to engineer and protect entanglement among qubits, turning what once looked like a philosophical embarrassment into a practical resource. Many-body quantum physics shows that entanglement is not only a two-particle curiosity, but part of the hidden structure of superconductivity, superfluidity, magnetism, and complex quantum matter. At the same time, decoherence explains why the ordinary world looks stable. Warm everyday objects constantly interact with air, heat, light, vibration, and surrounding matter. Their delicate quantum relationships spread into the environment so quickly that visible interference becomes inaccessible. Quantum mechanics does not stop working. Its fragile patterns simply become hidden beneath the enormous complexity of ordinary life. Even black holes have drawn entanglement into deeper questions. Jacob Bekenstein and Stephen Hawking made information central to gravitational physics, the black hole information paradox, the holographic principle, and the anti-de Sitter conformal field theory correspondence suggest that information and entanglement may be woven into the relationship between quantum theory and spacetime itself. Some modern ideas even hint that entanglement may not merely exist inside space, but may help explain how certain descriptions of space hold together. Different interpretations still disagree over what is really happening beneath measurement. Copenhagen, many worlds, de Broglie-Bohm theory, objective collapse theories, relational quantum mechanics, and quantum Bayesianism each loosen a different classical assumption. Entanglement does not offer one comfortable picture that restores old common sense. It asks which part of common sense should be trusted least. And that may be its deepest lesson. Nature is not always built from isolated parts with independent properties. Sometimes the relationship between parts is part of the most complete description. The whole can carry physical meaning that cannot be recovered by treating each piece alone. The strangest connection in the universe does not make reality less real. It makes reality deeper, quieter, and less obedient to human expectation than ordinary life suggests. Entanglement shows that beneath the calm surface of the world, separateness is not always as simple as it seems.